Good morning. My name is Nerea Markaide, and I am the coordinator of the AIRPOXY project. On behalf of the entire consortium, I would like to welcome you to this workshop that we have prepared with such enthusiasm. AIRPOXY project was born to contribute towards maintaining the leadership in the European aeronautics industry through the development of new innovative materials and tools for novel composite materials. In addition to presenting the results of the project, today we will have the opportunity to learn from the hand of great experts the latest trends, challenges and opportunities that are being developed around the composite materials in the aeronautical sector. I wish you an interesting and fruitful workshop about these important issues. And without further delay, I will briefly review the day's agenda. We will start with a welcome from the hand of Andrés Catalán, who is the General Secretary of the Spanish Technology Platform. And afterwards, I will introduce the AIRPOXY project. We will start then with the material session that will be chaired by Alaitz Ruiz, head of the Polymers and Composite Unit at CIDETEC, that is here. At 10:40, we will have the first coffee break in the next door, where you can also visit the poster session that we have prepared by the AIRPOXY consortium. Sorry. Afterwards, we will continue with the manufacturing session that will be chaired by myself. At the end, we will proceed with the lunch that will be served as a cocktail, also in the next door. And then you can also visit the showroom where the materials and demonstrators developed in the project will be exhibited. In the afternoon, we will continue with the sustainability session that will be chaired by Alaitz Ruiz de Luzuriaga from CIDETEC, who is the main developer of the resins and adhesives in the AIRPOXY project that is here. And afterwards, we will continue with the panel discussion moderated by Elena Jubete, BDM of CIDETEC Surface Engineering, that is here also. And last but not least, we will end the day with a visit to CIDETEC Surface Engineering facilities, which are at 5-minute walk from here, and with a visit to the poster and showroom area. AIRPOXY project partners will be happy to explain and clarify all details and questions you may have. Well, let's start with a welcome from the hand of Andrés Catalán. Andrés Catalán is an aeronautical engineer, and he is, since November 2020, the General Secretary of the Spanish Aerospace Technology Platform, PEA. Before joining PEA, he worked on different leading companies of aeronautical sector, holding various positions such as project manager at CASA Space Division, head of system engineering and cost manager at Ibermisil, Vice President of Aeronautics Division and Head of the Business Unit at the Defense Division at EADS, and several responsibilities such as third-party management and the corruption program at the Defense and Space Division within Airbus. Andrés, I give you the floor. A ver. Ahora. Este lo apago.
In this workshop, it's always a pleasure to be in contact with people that is the real work now in working in the platform and useful to deal with the people in the big offices and the floor, but not in the real with the real people working. And for that reason, it's a pleasure, yeah, really work with you. Also, it's a pleasure to take the opportunity to visit San Sebastian. It's always a pleasure to be here. A very good excuse to come. So thank you for the invitation. Just to not be very boring with you, no? The technological platform. You know that in Europe there is an initiative a long time ago to have platforms to bring together all the stakeholders in the innovation ecosystem, from academia to labs to companies. And then this is one of the examples. Where the platform exists since 2006. And now gathers about 107 members in Spain. Airbus is one of the main stake players here, and with a lot of pushing a lot. Also, tiers one like Aernova, which is one of the speakers, or Cituri. So there is a lot. The main companies working in aerospace in Spain are here in the platforms. And then we have two mandates to deliver it, to bring to administration and to the society in general. One is to promote the contact and the connection between all the players, and this is one we normally do. And the second is to produce the strategic research agenda, and this is you like it, what the administration likes more. So to have one text explaining what, as technicians, we would like to develop in the future, and this is the document that they normally use for the technological plans the CIDETEC and Ministry of Science produce. We have done this, and we have elaborated this nice document here, the strategic residual agenda for aeronautics. We have a second volume for space as well, and the document is we have 148 strategic technological lines that we have discovered, distributed among these 5 main challenges: what the market demands, of course, always competitiveness, sustainability, and zero emissions aviation, safety and security, always in aeronautics, and the institutional support. One of these, in the challenge of competitiveness, one of the lines that we have identified so when the agenda was launched, that was in 2019, in a ceremony with the Ministry of Science at that moment in time, was to develop advanced composites with the trend to lower the cost, to implement flexibility in the production, to take advantage or to deal with the advanced material and so on. So it was exactly what you have done. So congrats for this trend. This is one. So I could say that we have already seen in the document. So you have done. Next things that we see in the future. No, we have new challenges for you when you finish this project. The new one is. You know, the hydrogen in the aircraft. No? So, well, the hydrogen, it looks like the best solution in the future for the mobility. In aviation, it looks like yes, yeah, it could be. For sure, it will be a propulsion without carbon emissions, so very good. But it puts a lot of challenges in the aircraft. So we have to the hydrogen has to be in a liquid form. So we have is liquid hydrogen. This is 270 degrees of below zero. That puts a lot of pressure in the design of storage. Today, the people is working in having something in composite also, because the deposits are big. So we need to also to look for the weight. But the areas are the volume is also high. All the configuration of the aircraft will most likely to be changed. So this is really a big revolution, not only in materials, but also in configuration of the aircraft. So this is a good challenge maybe for you when you finish and you complete the project. This is the next step. And this is one a chart that I copied from one of my colleagues in ITP. I love this because it's always our story. So we start to do things, and the end is never. We never reach the end. So there is always something more to do, and this is good for us, no? So we have good things to do. Well. For me, it's enough.
Thank you, Andrés. Thank you, Andrés, for this nice welcome. Yes.
So I was in time, and then I give the floor to Nerea Markaide, the industrial engineer and coordinator of this project. He's working with polymers and in the composite department at CIDETEC. She worked as a researcher in
maybe the
research center and participated in leading more than 30 private, national, and European projects, mainly related to thermoset matrix composites, and nanocomposite material and their processes. In 2010, she moved to Gamesa Eólica when worked during 3 years as a senior engineer in the composite department. And in 2013, she joined CIDETEC as senior research, where her research interests are focused in the processing and characterization of composites with tailored properties.
Thank you, Andrés. Okay. Well, so I will explain. I will summarize the project very quickly, because afterwards my colleagues will explain you more in detail different activities. So the title of the project is Thermoformable, Reparable and Bondable Smart Epoxy-Based Composites for Aerostructures. These are the topics that I'm going to present. Firstly, a brief introduction to the project, then the technical approach we have working on, afterwards a summary of the main outputs, and finally the next steps. The project has been financed by Horizon 2020 program within the topic focus on the maintaining industrial leadership in aeronautics. The project started in September 2018 with an initial duration of 42 months, which has finally been extended to 48 months due to the delays generated mainly by the pandemic. The consortium is composed by 11 partners from 6 European countries. UNE, Eurocat and IDEC and CIDETEC from Spain, Aire Composite from Ireland, Alter and Arctic from France, SONACA Co-Expert from Belgium, LEIBNIZ IVW from Germany, and the Department of Material Science and Engineering of the University of Ioannina from Greece. The consortium has been supported by a strong advisory board with relevant representatives from Huntsman, SGL Group, Leonardo, Airbus, and EREA through INTA. The main objective of the project is to reduce the production and maintenance cost of composite parts in the aeronautics sector by developing and introducing what we have named 3R composites that are based on 3R resin. These 3R resin for aeronautics sector have been developed in the project, and they are epoxy resins that below its TG have the same properties as typical epoxy resins, but above the TG the chemical network becomes dynamic, and in this moment the resin has a thermoplastic behavior. So the resin has the advantages of the thermosets in terms of mechanical and chemical properties, and also the advantages of thermoplastics in terms of processability, being reprocessable, recyclable, reparable, and also weldable. This is possible by replacing the typical amino hardeners used in the epoxy resin by anaromatic disulfide hardener. The resin produced with this chemistry are called vitrimers. CIDETEC started working on these materials in 2013 to develop industrial-grade 3R resins. And now, in our AIRPOXY project, we have jumped into the aeronautical sector. The project focuses in 4 technical objectives. The first objective is the development of a 3R resin that, being reparable, reprocessable, and recyclable, meets the aeronautical sector specifications. Sorry. Okay. The second objective is the development of a 3R thermoforming process that allows high-volume productions faster and cheaper than autoclave. The third objective is the development of 3R repair process that, combining with structural head monitoring technologies, allows early detection of delaminations that can be repaired by easy and fast repair methods. And the fourth objective is the development of 2 3R bonding processes, one based on the welding of 2 3R substrates that will be faster than conventional bonding processes, and one based on the conventional adhesive bonding process, using for that a 3R adhesives that allows to increase the bonding robustness when bonding 3R substrates. There are 2 other cross-cutting objectives, one related to the environmental, economic, and human health risk assessment, and the other related to dissemination and exploitation activities. To achieve these objectives, it was established a work plan divided in 8 work packages. Work package 2, 3, and 4 are related to the technical development of the 3R technologies to a TRL 4. And work package 5 is related to the validation of the technologies, I don't know why it moves, in industrial environment to a TRL 5. For that, 2 demonstrators were selected, a subcomponent of a representative fan coil formed by a skin, transverse stiffener, and longitudinal stiffener, and a subcomponent of a representative leading edge formed by a nose and 2 webs. The main materials and processes developed in the project are summarized in this table. Regarding the materials, firstly, the aero-grade 3R resin was developed as a raw material, and based on it, several intermediate products were also produced, which are laminates, enduring prepregs, resin films, and adhesive films. All these materials were used to develop or optimize several 3R processes for composite production, bonding, and repair. Regarding the composite production, the processes studied and optimized were the RTM, thermoforming, and SQRTM. Regarding bonding, the processes approached were the welding and adhesive bonding. And regarding repair, the processes were structural health monitoring combined mainly with hot compression. And also simulation tools adapted to the characteristics of 3R resins and composite were developed for thermoforming mainly, but also for adhesive bonding and repair technologies. So as a result, several outputs summarized here have been obtained. Now I very briefly will show some details of each of them, but afterwards, as I said, my colleagues will present more in detail through the talks and the posters that also they have prepared and that you can see during the day. Well, regarding the 3R resin, based on the specifications that the epoxy resin must fulfill for aero sector, several formulations were prepared and tested. And after the first screening, it was selected the reference as IRES 7 as the most promising one. Its viscosity and curing cycle were adjusted to be suitable for infusion and resin transfer molding processes. And the resin can be prepared as, and supplied as 1 component or 2 component version. Also, the dynamical behavior of this resin was confirmed. and validated by performing several dynamic mechanical tests to measure the relaxation time and stress relaxation at different temperatures. The thermoformability of this formulation was validated also, and for that, a resin plate with a TG of 170 degrees was successfully thermoformed at 200 degrees. Afterwards in the showroom you will see this plate, thermoform plate. And also the resin was mechanically characterized to confirm the properties. In this table you can see only some of the results of some characterization. Tests were performed at room temperature and also in 2 different hot-wet conditions. Well, based on this resin formulation for thermoforming, several intermediate materials and processes were tested. We work in mainly 2 different strategies. The first strategy consists of the thermoforming of the fully cured 3R laminates in a discontinuous process, similar to the thermoplastic organosheets. And in this case, the laminates were produced by RTM process because it was easy, because we had the resin was ready for this process. And in the second strategy, this consists of thermoforming the enduring prepregs in a continuous process. These enduring prepregs were produced in a classical impregnation process, but in this case the resin was procured to about its gel point, so it is dry, it is not wet, tacky. In this way, the material can be stored at room temperature, which is a very interesting advantage. And with this enduring prepreg, during the continuous compression molding, the enduring prepreg plies are first pre-consolidated and then they are thermoformed. This option, of course, is suitable for the production of geometries with a symmetrical section, such as an omega profile. Later you will see a demonstrator. For adhesive bonding, also based on the specification of the aero sector, different formulations were prepared and tested. And after the screening, in this case, it was selected what we reference as AIR-22. The viscosity and curing cycle were adjusted to be suitable for the production of the film in a continuous process, and later bonding using vacuum bag method in this case. And this adhesive is supported by a polyester mat. Also, you will see some sample in the showroom. Once optimized and validated the production process of the film, it was used to produce several specimens for testing. The substrates used for that were also 3R laminates, and well, in this table you can see the results that we obtained in the single lab shear strength test at room temperature, also and at 120 degrees after conditioning. For welding technology, it was formulated a 3R resin film, very similar to the adhesive film, but with some difference, because this film was added in the surface of traditional composite panels during the production using the SQRTM process. And in this case, the film was formulated to be suitable, on the other hand, for the SQRTM process, and on the other hand, for the welding process using hot compression afterwards. In this case, this film is supported by a glass mat. Once produced the film, in the continuous process, it was integrated in the SQRTM process to obtain traditional panels with the 3R film on the surface. And afterwards, it was studied also and optimized the welding between these panels and RTM panels produced with, of course, with a 3R resin. And the welded panels were tested. In the graphs, you can see some results of the single lab shear test. Regarding the repair, firstly, the knockdown effect between the 3R resin and conventional resins was assessed combining different material configurations, mechanical tests, and non-destructive techniques. On the other hand, the repair process also was studied It consists basically on applying heat and pressure on the 3R laminate where the laminations have been detected. Parameters like pressure, temperature, and time were studied. And finally, the knockdown effect and repair efficiency of the 3R composites were assessed. An example in these graphs are included some of the results obtained on RTM laminates damaged under low velocity impact and interlaminar shear strength test, and that afterwards were repaired and again tested. The results showed a repair efficiency of 84% in the case of low velocity impact and 67% in the case of interlaminar shear strength. All the materials and technologies presented until now were validated through the manufacture of 3 demonstrators. The fan coil and leading edge were the 2 demonstrators selected at the beginning of the project, and the Omega profile was the 3rd demonstrator that was decided to carry out to validate the thermoforming capacity of the 3R material in a continuous compression molding process. For the environmental and economic analysis, 5 study cases were defined and analyzed by EURECAT, comparing the 3R technologies with the technologies used today. The manufacture of the leading edge and the fan coil was also analyzed from the point of view of human health risk by EURECAT, also considering 2 scenarios, the inhalation of fibers and the inhalation of volatile organic compounds. I would like also to mention several activities related to dissemination and exploitation of the results. Coordinated by EIRE, a technology bootleg was prepared where the steps undertaken to develop the 3R technologies are reflected. You can find a copy in the folders that you have received during the registration. Also coordinated by EIRE, a business model canvas is being created to find the most relevant market segments for the aeronautical sector, to identify the competition and customers and the way to reach potential customers after the project. Also coordinated by CIDETEC, a feasible roadmap to complete the full development and certification of the 3R technologies is being defined. And also a workshop agreement has been drafted by the University of Ioannina, coordinated by UNE, and finally approved by the European Committee for Standardization. This agreement describes a test method for the evaluation of the adhesive properties of fiber-reinforced polymer composite joints, and it has been very recently published, and it is already available free of charge through the webpage of the committee. And finally, the next steps. The AIRPOXY project has focused on the progress of 3R technology to enable a higher degree of maturity until tier 5. Additional research, of course, will be required to continue advancing in the development of technologies until the final industrialization. The AIRPOXY project has focused on advancing the 3R technologies to enable a higher degree of maturity up to tier L5. Therefore, further research will be required to continue advancing in the development of technologies until the final industrialization. And that's all. Thank you for your time. And well, if you have a question, I can answer now, or we can discuss during the next presentation. Thank you. Okay, and now let's continue with the agenda. So let's continue with the agenda. So we will start with a session dedicated to the new materials. Este es su Harry. The session will be chaired by Alaitz Recondo, Head of Polymers and Composite Unit at CIDETEC. Alaitz has a PhD in polymer chemistry, and before joining CIDETEC, she worked for 6 years as a researcher in the R&D department at industrial company focused on the development of silicone and polyurethane-based sealants and adhesives, where new sealants based on silanized polyurethanes were developed and industrialized. She joined CIDETEC in 2011, and since 2017, she's the head of Polymers and Composite Unit, where one of the main research activities is focused on the development of dynamic polymer networks based on reversible chemical bonds. So, welcome, Alaitz.
Thank you, Nerea. Good morning to everybody, and I would also like to thank you, on behalf of CIDETEC, attending this workshop. Okay, now we will start with the first session of this workshop, which is entitled New Materials, and there will be 4 speakers. I will ask all the speakers to please fix the time in order not to be late. The presentations will last 20 minutes, including the questions. So if we have time for questions during the presentations, okay, and otherwise we can leave the questions for coffee break or lunchtime. Okay, so now I will present our first speaker, José Sánchez, PhD chemist, and today retired from Airbus. He worked for Airbus for more than 37 years, always in composite area and for all military and civil aeronautical projects, with main activities in composite materials development and qualification, as well as composite technologies development and in-service support. During this period, he had different positions, and more relevant ones was head of composite materials in Airbus Commercial and Central Technical Authority in composite field, and composite executive expert for Airbus Group. Thank you very much, José.
Thank you. So many thanks, Alain and Nerea, first for the invitation to come here, and second for your kind presentation. I will try to cover a little bit what is the today's situation with the composite material in the market, and what has been the history, and especially what will be the future. The first item is when you can see the screen, you see what is the evolution of Airbus. This figure appeared in many presentations in the last year, but when we are looking to this page or to this screen, looks easy, the introduction of composite material in the market, seems step by step with no problem, but the reality is every step we have to change, we have to manage many different subjects in Airbus. The first subject that we have to manage to be sure that when we want to introduce a new material, we have the technology available. Second one, that the cost of the solution is good enough. Second one, every new step we have to see what is the perception of our operator and what is the in-service behavior of this solution. More important also is that we have the industrial setup internally, but also externally. And externally is very important because at the same time that we introduce composite material and technologies in Airbus, we develop an industry around us, industry related with machine, with the material, etc. And finally, we have good methodology covering stress and design in order to allow to make good parts. Looks easy, but at the end it's a very complex process, working together with universities, central technology area, industries, and regulator in order to have a good solution for the benefit of the aircraft. This has been very complex, but the reality is that today we are in the area of 53% of composite material. Not only Airbus, as you know, also Boeing reached this target, this value, but the principle of Airbus is only go step by step. And this step by step means introduction of new material, new technology, new solution, and I can assure you that during this period of time, we have introduced many different technologies in our aircraft. And maybe the reflection today is that, fortunately for us, the methodology at that time was not the one that we have today. Because if we have to use the today methodology in our company, means TRL review, MRL review, etc., many of these parts never has been done. So for me, the first reflection is something we have to do if we want to introduce new technology in our companies. In other case, will be more and more difficult, not because we don't have technology, it's because we have to take some risk. And during this period of time, many introduction of many parts, fuselage section, wing skin, HTP, movable, sandwich structure, monolithic, occur, co-bonding, etc. In many cases, we take some risk. Controller risk, but risk. Today, it's absolutely impossible. So I can imagine, I think I saw Timo and Caroline here, I can imagine many of the today technologies and the development in Airbus that absolutely impossible to be introduced, absolutely impossible. So it's a reflection for the management of this type of technology development, because or we take some risk or never we will introduce new technologies in the market. This is the today situation in Airbus, but where are our competitors? And when I said our, I have the feeling that I am still working for Airbus. Boeing is introducing new wing in 777X, but it's more or less in parallel with Airbus. So this means that the new project, they are making the wing. Don't forget that 787 was the wing and the complete fuselage. In the 777 was only the wing. Our Russian colleagues, UAC, again, the same subject, they introduce a new wing. In this case, instead of prepreg like Airbus or Boeing, they make a technology based in infusion with dry tape, okay? But again, only the wing and movables. Bombardier, today Airbus, again, is the same. The wing is a composite part, but the fuselage and many other parts, again, metallic material. In the case of Bombardier, the wing is an infusion, in this case, non-cream fabric and manual operation. And in the case of Comac, the Chinese colleague, with the new C919, as you know, the complete fuselage and wing is a metallic structure. So they are making the HTP, BTP and movables, but again, you can see a reduction of composites used in the new program. And even worse in Embraer and Mitsubishi. Mitsubishi is even worse, because Mitsubishi Heavy Industries is the company making the wing for 787. So the market is waiting that Mitsubishi will propose a lot of composite in the aircraft, even if it is a small one. The reality is the contrary. Most of the aircraft is metallic. Why? Due to cost, mainly. At the end, I have a reflection, the preliminary one. First of all, composite material today are a state-of-the-art material. It's not the new material that is coming, it's the material that we have. But also at the same time, you can see in the new program that metallic are coming back. And are coming back due mainly to one subject, that is the cost of the solution. So cost is the key driver for the future. And when I said cost, I don't say the last sentence that maybe is related with your project, with CIDETEC project, well, CIDETEC AIRPOXY, that is related with the reuse, recycling of the material. That for me, as we will see at the end, is the key sentence for the future of composite material. So metallic is coming back, as you can see in many programs, and we will see in Airbus and even Boeing. And the step-by-step introduction is a clever approach in order to understand the problem, to develop technology, to develop industrial solution, and to get a good solution for our operator. Finally, just to say that the history of composite is an history of success. It's a very good history. We have all the operators in general are happy with our solution, with only 3 exceptions. One is the sandwich, very well known by all of you. I think that we have to recognize that we have many problems in the past, not only Airbus, also Boeing, Douglas, and many others. We have many books about this subject, and if you are interested, I will be very happy to explain you what are the problems during the coffee break or during the lunch. Second one is the structure with dissimilar material is something that we have to take into consideration because could be a problem. And the final one, some cases of bonded structure, Timo, I showed you, and we suffered together during many years with this, not only Airbus, also Boeing and many others. Is why the authorities keep an eye about this type of structure, this type of solution, and is something that obviously we have to continue with the today's situation and even to continue with some development. I put a picture. Even if our solution is good enough, sometimes we have problem that appear time to time and we cannot avoid. This is a bird strike in a Airbus 350 recently. This photo was taken 3 or 4 months ago in Barajas, in Madrid airport, and it used to happen, not only for composite, also for metallic. Fortunately, aircraft is certified and calculated with this type of situation, but the pure bear don't survive, I think. So the first consequence is that we have to keep today a strong effort in development of material, and composite solution. Don't think that the composite will be forever. Metallic, as you saw, are coming back. And if we want to keep our industry, we have to make a huge effort in development of new solution, taking into account the cost and circular economy. These two sentences are and will be key for the future. Well, this is an overview of our today 3 main areas of development in composite that are thermoplastic prepreg, infusion technology, and prepreg, infusion, and thermoplastic. The 3 are still valid. Some of them, or one of them, are the more relevant in Airbus and Boeing. The other one is relevant in Airbus and Boeing, but more relevant in other companies. And the last one, thermoplastic, has been a promise during many years, are a promise today, and as some colleagues in USA said, will continue being a promise in the future. We will see what is the reality with this type of material, but my feeling is that at the end, what we will see in the future crisis is a combination of the 3. So we have to find the good solution for the different areas. These are the 4 lines of development for composite material and structure. The first pillar is cost reduction, as I said, and this cost reduction has to come for the pure material. The second one is improved process, again, in order to reach better productivity and, as a consequence, cost reduction and improved quality. The next pillar is reuse and recycling, and is key, as we will see later. This is something that, in my opinion, or we solve the situation, or better to find a different business, because during the last evaluation of technologies, and I can understand, is a must. This subject is not something that we should do it. In my opinion, is a must, and is room for improvement. Even if we have some partial solution today, especially in Japan, UK, and USA, also in Europe we are working, but clearly we need a strong development in this area in order to find a realistic solution and with some added value for the final solution. We can put the scrap material in the roads, but I have the feeling that is not the solution that we are looking or we try to develop today. And the final one, not the final, but also very important, obviously we have to think about to improve performance of the material in terms of mechanical properties and other properties, and to provide multifunctionality, added value to the solution. This multifunctionality, I don't see a strong development in short term, but I see a strong development in medium term, and will be the different, and one of the key subjects we want to continue fighting against metallic solution. In the area of material cost, I can see many different subjects that we can work, starting with testing. For me, testing is a key subject. In my opinion, during production and also during qualification and certification, we are over-testing. And today we have room for simulation technologies. We have to find a compromise between simulation and testing, and it's something that we have to combine and to discuss with our authorities in USA and Europe. During some discussion with the American authorities, they told me something that very nice, but continue making testing. Come on, it's time for some development. Even if I can understand in some areas like bonding, it's obvious that we have to continue making testing. In other areas, we have enough experience. We introduced composite material more than 50 years ago. I think in 50 years, we have experience. We can try to make something. I think it's to continue making exactly the same quality control and certification and qualification tests. I can see some improvement in this area. But also, this testing, reduce of testing implies reduce of scrap material. And for me, the reduce of the scrap material is a key subject for today and for tomorrow. Additionally to this, room for development a new formulation, and I saw when in your presentation, Nerea, a key subject in my opinion. This type of development like the bitrimers is key for the future in order to improve our formulation. And it's obvious that the best solution is a combination of effort of industry, material supplier, universities, and technical center. And this will be the only way in order to develop new technologies that will assure our future, again, in a cost-effective, with the possibility to improve the manufacturing of the material, but especially to allow some technologies to reduce scrap. And for me, scrap reduction and reuse and recycling should start from the design of the material and the design of the structure. If we don't take into account from the beginning of the process, later on will be absolutely impossible to have a good solution. And it's something that we have to explain to our project manager, to our designer, that or we find a good solution from the beginning and later on it's too late. If you visit a company like Tarmac, I don't know, in France or in Teruel here in Spain, you will see that it's impossible to make a good recycling when you have the complete aircraft. You need to take into consideration from the beginning, from the design of the complete aircraft. Okay. Just some word due to the time that I don't have a lot of time. In the manufacturability of the material, again, room for improvement in testing and in many other areas. But just 2 sentences for me is the one that I put in the photo. The first one is auxiliary material, something that, in my opinion, the best of the auxiliary material is no auxiliary material, because at the end we are scrapping very expensive material. Even if for aerospace is a very cheap material, for the other business is a very expensive material. So it's incredible the tons of material that we are scrapping, and obviously we have to find some solution. We have some patent in Airbus what to do with this material, but again, room for improvement and room for development. And the second sentence is a personal reflection. Again, is why we are using only one material type and grade in one part. What we can use, why we cannot combine different grades or with different material in the same part. And again, room for improvement. I put a photo of Torres with a machine rated with the possibility to change the head of the ATL or fiber press machine, and in this area we can combine different grades of material in terms of thickness, width, even fiber, even resin, etc. with the at the end for the benefit of the cost reduction, scrap reduction, and performance and weight of the part. So for me, it's an area that we should continue working and continue developing. Multifunctional material, very fast in order to allow some time for questioning if you have any. Again, clear that we have to make something, but in this case my reflection is we have to try to find multifunctional material with several solutions. I cannot see added value only one. Why we don't combine more than one? Okay, some ideas in this area, but again, room for improvement and room for work in the future. In the area of reuse and recyclability, as I said before, this presentation has been done in combination with my colleague Tamara Blanco, that I shared this presentation with her. And thank you first of all to her. And again, auxiliary material for me, when I saw the tons of material that we are scrapping every day, for me it's painful. And we are not scrapping minor material, we are scrapping polyester, nylon, glass, polyethylene, many type of sealants. It's absolutely painful and incredible that we are scrapping this type of material, tons and tons every day. And when I said the scrapping, I mean landfilling, room for improvement. But even worse, the number of material that we are scrapping, the structural material. We are paying a fortune per kilo of composite material, a fortune. And in some parts, not only Airbus, this is a general, we are scrapping 40% of the material. 40%. 40%. This is absolutely unacceptable. So it's true that in Airbus we have made a huge effort, and Boeing make exactly the same, changing the format, changing the type of the machine, the width, the thickness, in order to reach a realistic target that we are maybe in the area of from to 10%. Is acceptable, but at the end is very high. Can we do something? Yes. We are scrapping from the testing. The scrap material due to the bad quality, trimming, spire material, many different areas that we can improve with the target to reach zero scrap material. Is possible zero? Maybe too aggressive, but to reduce dramatically the value, not only possible, it's necessary. Okay. And just to finalize, and due to the fact that I don't have time, some conclusion. First of all, composite need to compete against metallic. This is a key subject for today. We are not the winner of the history. Seems to be, but when you can see what is happening today in the market, is not the case. The metallic material are also working with good solution. And I see just a small joke. I used to meet during many years my colleague in Airbus, the head of metallic material, in the past Loren Pinto, today Rafael Peraldi. And I saw Rafaela some weeks ago. And every time that I saw her, I used to tell her before hello, what about the corrosion of the material? Rafael, are you still corroded? Or Jose, you are always making joke. But 3 weeks ago, when I saw her, before to tell her hello, she told me, hey, Jose, what about the recycling of the composite material? Are you still unfilled? Rafael, are you making jokes? So you can see the history changing. Until now, we are the winner in front of the metallic. We are the arrogant people in front of them. And if we don't take care, in some years, will be exactly the contrary. So metallic material are coming, and for this, a strong development. Again, I saw your development, Nerea. I'm more than impressed. This is the direction that we have to follow for the benefit of the industry, of the composite industry in the future, especially in Europe. It's for the world, but Europe should be the leading area of this type of technology development. Second one, and it's very important due to today's situation in the world, supply chain. Fortunately, and I said fortunately, we're in a good situation. Our supply chain, fortunately, is based mainly in Japan, USA, and Europe. Fortunately today, it's not the case of our metallic colleagues, and it's a good area in our area, but we have to take care. It's something that we have to change our mentality for the future. The situation that we have today due to the COVID and due to the war, who can imagine, but is here, and it's something that we have to continue working in this area to keep, or to at least to think what will be the future in this area for the future. Step by step, as I said before, and reuse and recycling. Reuse and recycling is a must, and for me, is something that has to drive our direction, our future, our development. But starting, as I said before, from the beginning of the program, we had to convince our project manager and all the technical director, the technology director, that or we solve this problem and better to find another job, metallic or whatever you can imagine. Okay, thank you for your attention. Sorry to be a little bit late.
Thank you, Jose. Very, very clear and interesting. We can have a couple of questions if you have, or for later on during the
The
coffee, because
coffee.
we are having the coffee, and during lunch we can have.
Many thanks.
Thank you very much. Okay, our next speaker is our colleague from CIDETEC, Alaitz Ruiz de Luzuriaga. Alaitz has a PhD in polymer chemistry. Currently, she works as a project manager in polymers and composite unit at CIDETEC. Her research is aimed to the synthesis and characterization of dynamic polymers and composite materials for different sectors. She is co-author of more than 20 scientific papers and inventor of 3 patents related to dynamic thermosets. She has been involved in many R&D projects related to dynamic thermosets, and in epoxy project, she is Work Package 3 leader, and now she will present the most relevant results regarding the 3R materials and intermediate products that have been developed in epoxy project.
Okay, then I will continue with some basic concepts to better understand what are dynamic thermosets, to end with some applications, conclusions, and future prospects of this technology. Okay, as José Sánchez already explained in the previous presentation, composite materials have played a major role in weight reduction, and they are used for both structural and manufacturing of many compounds. It is said that aerospace composites market was valued over 12.7 million United States dollars in 2019, and is estimated to grow of more than 9% from 2020 to 2026. But so it's clear that the product manufacturers are heavily investing in the research and development in order to obtain innovative materials for the aerospace sector with good mechanical and impact properties. But as I'm going to repeat many of the concepts, I think, but José has perfectly explained. But despite the several benefits of these composite materials, they also show some drawbacks which are limiting their introduction for some applications in the aerospace industry. And here we have some of these limitations. One of these limitations is that the high level of security and safety of the aviation structures demands testing aerospace composite at each step. And also the expenses for that testing are huge, which is leading to skepticism in the use of composites for some applications. Also the high cost of the raw material, such as carbon fiber, and together with the high manufacturing cost, can hinder this predicted market growth. Another problem of this material is that the repair is quite difficult and it's very expensive. So also structural health monitoring techniques are needed in also to reduce all these maintenance, repair, and operational costs. And the main problem nowadays is that they are not recyclable. So why AIRPOXY project? When we were analyzing all these drawbacks, and we start thinking, and we proposed this AIRPOXY project with the aim to solve all these limitations and increase the use of the composite materials in the aerospace industry. So, as Nerea said, one of the main objectives of the project, AIRPOXY project, was to reduce the production and maintenance cost of composite parts in the aeronautics sector by introducing this 3R composite. 3R means reparable, reshapable, and recyclable. And we have another specific objectives that were to increase the the volume production of these materials, to have an easy reparable materials with high thermal and mechanical properties, to develop new bonding technologies for easy assembly, disassembly, in order to repair easier these composite parts. Also repair of the 3R joints by hot compression molding techniques, and also to have weldable materials. So to reach all these objectives, we had to select which material would be the most promising one. So we start thinking on a thermoset composite or a thermoplastic composite, thinking in which will be the most promising one. But when we start to analyze the different materials available, if we compare both thermoset and thermoplastic materials, both of them show some advantages and disadvantages. So if we analyze thermoset composites, due to their thermoset nature, these composites are not suitable for high volume production. The repair is difficult and they cannot be welded, but in contrary, they offer very high thermal and mechanical properties. On the other hand, thermoplastic composites allow for higher volume productions. The repair is easier, they are weldable, but the thermal and mechanical properties are worse than the thermoset composite. So to achieve all the goals defined in the AIRPOXY project, it was clear that a new material is needed. And this new material is what nowadays it's called a bitrimer material or composite. These materials offer all the advantages of thermosets and thermoplastics because they allow higher volume productions, easier repair, high thermal and mechanical properties, and also allow welding techniques. So before starting with the work done in the project, I would like to introduce some basic concepts for the development of these 3R resins in the AIRPOXY project. So when we talk about bitrimers or covalent adaptable networks, one can ask what is a bitrimer or what is this a covalent adaptable network? So to better understand this, as we said before, if we compare thermoplastics and thermoset materials, thermoplastic are processable, soluble, and recyclable. But however, due to the presence of the crosslinks, the thermoset materials are not processable, they are insoluble, and they are non-recyclable. But contrary, they offer better mechanical and chemical resistance. So we ask, what about having a material which offers the advantages of thermosets and thermoplastic? So the answer to this question is having a bitrimer or a CAN material, a covalent adaptable network. So these materials can be categorized in two different types. What are known as dissociative covalent adaptable networks and associative covalent adaptable networks. In dissociative covalent adaptable networks, when an external stimulus is applied, there is a temporary loss of crosslinks, which results in a sudden viscosity drop. In contrary, in associative CANs or bitrimers, which are the materials that we are studying today here, the crosslinking density is always constant. So we have a cross-linked network always. but there is an exchange between the dynamic bonds traducing in a gradual viscosity decrease. So bitrimers are permanent networks connected via dynamic covalent bonds, which allow the network to change its shape or its topology while maintaining a constant chemical bonds at all temperatures. So, what is a bitrimer? We have to have in mind that a bitrimer is a new kind of synthetic polymer which are 100% recyclable. They are covalent networks with a high degree of cross-linking, and they are reprocessable after curing above their TG. And we can tune these mechanical and these properties, and we can have materials from elastomers to high modulus resins, and we can tune the thermal properties of these materials. But we have to take into account that bitrimers, they are not a thermoplastic material, since they are cross-linked materials, and they are not classical thermosets, since they are reprocessable after curing. So, before starting with the 3R resin development in the AIRPOXY project, all the AIRPOXY partners defined the resin properties for the aeronautics sector and for the project. So the AIRPOXY resin must fulfill all the specifications defined in this table, but it needs to be also reprocessable, reparable, and recyclable. So we need to design and reformulate these networks which contain the dynamic covalent bonds, and for that we needed a dynamic covalent chemistry which is compatible with the epoxy resins. We need a low viscosity epoxy precursor. We analyzed that we need a tetrafunctional epoxy resin in order to have a high TG and reduce creep at high temperatures. We need short stress glaciation time, the degradation temperature as high as possible. And also we need, to achieve all this, we need a dynamic covalent bonds. And this new technology has to be simple, readily available, highly efficient, scalable, and cost efficient. So, with all this in mind, we studied the existing strategies to prepare bitrimers. And here you can see different strategies that are known nowadays to prepare these materials. And for this project, we selected the step growth polymerization strategy because it's the reaction that occurs in classical epoxy resin. So now we have the strategy, but then we had also to select this dynamic chemical bond. So we started to study the available exchangeable chemical bonds. And after careful analysis and the previous experience of CIDETEC with these dynamic materials, we selected the aromatic disulfides as dynamic bond to design this 3R resin because the materials are commercial, they are readily available, and offer many advantages among other 16 ones. So we started with the project, and Huntsman supplied us different epoxy resins, and we started to prepare different mixes, and we mixed these different resins with the selected dynamic hardener in order to achieve all the specifications defined in Work Package 1. So in order to obtain an aero-grade 3R resin, we prepare 9 formulations, and we characterize. In this table you can see the pre-screening that we did with these 9 formulations. So we studied different mechanical and thermal properties, and according to perform screening test, we selected what we called in the project IRS-7 formulation, because this formulation fulfills all or most of the specifications defined in Work Package 1 by the AIRPOXY partners. So we obtain, we have this resin, we characterize, and here you can see that we compare this the mechanical properties with the RTM6 resin, which is widely used in the aeronautics sector, and we can see that we obtain similar mechanical properties to RTM6 resin. Also, we characterize the thermal and dynamic properties of the resin, and we observe that this resin was stable until 220 degrees, and also we define the thermoprocessing window of this resin, and we conclude that this resin can be thermoformed between 200 and 220 degrees. Here you can see that we also manufacture some composites with this resin, and we did a complete characterization with these composites, and we also conclude that the mechanical properties are similar to aerograde RTM6 composites. But this composite is also processable, reparable, and recyclable. Another objective of the project was to obtain a dynamic 3-air adhesive for easy assembly, disassembly, and repair of composite parts. And here we proceed in a similar way to 3-air resin. First, we defined the specification, and then we started with the adhesive. We formulated different 3-air adhesives, and with the selected formulation, we prepare a 3-air adhesive film in a continuous preparing machine, as you can see here in the picture in the right. In the figure below, you can see a single lab shear specimen which contains the dynamic epoxy adhesive, and as you can see here in the video, above the TG, above the activation temperature of the adhesive becomes dynamic, allowing such unprecedented properties such as repairing, debonding, and recycling of the adhesive. In this slide, you can see the defined specification for the adhesive at the obtained values, which are good. And finally, I'm going faster because I only have 5 minutes. In this slide, you can see the application of these developed materials. With the developed 3-air resin allows new functionalities which are not possible with conventional thermosets, and these composites can be obtained by RTM. They can thermoform. The repair of the laminations is also possible by applying heat and pressure, and the recycling is also possible. We can dissolve the matrix and recover the fiber with good properties. Also, these materials permit to well cure the composite parts. Due to the dynamic character of the 3-air adhesive, the bonding of the composites is also possible, and these composites, the bonded parts can be repaired. And now a detailed explanation of these applications will be made by my colleagues of the AIRPOXY project in the following presentations. So about the conclusions of this work, we can say that we have developed an aerograde thermoset with a TG of 170. This resin permits to speed up the current thermoset manufacturing processes. This resin have similar properties to widely used RTM6 resin. We have obtained a debondable adhesive with high TG and lab shear strength of 20 megapascals. We have developed a methodology for easy debonding and repair. And we have a recyclable material But how about the future prospects and the limitations of this technology? But even if significant progress has been made with these materials, we already know that we also have many challenges that should be addressed in further projects or in further, I don't know, projects, yes. We need to achieve shorter relaxation times at lower temperatures. We realize that we need to increase the thermal stability of these materials. We need to optimize and to increase the welding strength of these materials. And also it's a must to optimize the recycling loop of these materials. And thank you for your attention. I hope that you will find this presentation useful. And if you have any question, I will be happy to answer them. Thank you.
So now, Stefan Weidmann from IVW will be the next speaker. Stefan studied mechanical and process engineering at the Technical University of Kaiserslautern. Since 2017, he has been a scientific employee at the LEIBNIZ Institute for Composite Materials in the Manufacturing Science Department. And in AIRPOXY, he's working on process development of thermoforming, welding, and repair processes. Thank you, Stefan.
Okay, today I want to present you the 3R therming strategy developed in AIRPOXY, and the content of my presentation is first motivation, and afterwards I will give you a short overview of the basics of thermoforming, and then we'll continue with the lab scale thermoforming, and also then the introduction of industrial scale thermoforming in the discontinuous compression molding process, and then in the continuous compression molding process. And I will finalize my presentation with the conclusion. Okay, but first we'll start with the motivation of the processing advantages of thermoforming. So thermoforming provides short cycle times and is also suitable for automotive processing. And thus, it's also economically efficient mass production process, and also the tool wear is very low. And as it's possible to process continuous fiber reinforced polymers, the parts are suitable as structural parts. The advantage of the 3R FRPCs, as already mentioned, are the high lightweight potential, so the high stiffness and at the low density, and also the recyclability. And also, the 3R materials allow multiple processing, and by using different fiber reinforcements and additives, it's possible to tailor their properties. And due to the fully cured state of the 3R materials, it's possible to store them to an infinite length, and also the material provides good mechanical, chemical, and corrosion resistance, and are furthermore weldable and repairable. And as no additional solvents and so on are used, the workplace pollution is pretty low. Okay, before showing you the investigation we performed in the project, I will explain you a little bit the basics in thermoforming. So when the matrix polymer, when the viscosity of the matrix polymer is low, this may lead to a ply warping or fiber buckling because the layers are not allowed to slide off from each other. When the viscosity of the matrix polymer fits pretty well, this allows ply gliding, and the path of the fiber reinforcement is stable, and thus the mechanical properties of the part are pretty good. If the matrix polymer viscosity is too low, then this may lead to a matrix penetration and thus poor part qualities. When you design a mold in thermoform, you always have to consider some spring-in or spring-back effects, which may occur due to, for example, an introduced stress by the forming or thermal stresses caused by the cooling in the mold. In a microscopic scale, there are also fabric shearing effects, so the shearing of the fibers and the rovings, and also the elongation of the fabric during the forming. And also, as already mentioned, the ply sliding is a typical effect in thermoforming. At the very beginning, we investigated the spring-back and spring-in behavior of the 3R materials. Here, we put a neat resin, so without a fiber reinforcement, into a 3-point bending setup and heat the specimen and the whole setup in a temperature chamber up to 200 degrees. After the specimen is fully heated, a stamp deflects the specimen by, here in this case, 2 millimeters, and the holding time in this state was varied. And after the different holding times, the stamp move away from the specimen, and then the spring back of the specimen was measured. And the experimental setup in real you can see here, and the results are plotted in the diagram. And as you can see clearly that the result is that a higher holding time in the deflected state releases the stresses in the specimen, and the spring back is reduced. So when you see in the diagram a spring back of 0%, no spring back occurred. And this result leads to the assumption that the 3R resins need time at the forming temperature to adapt the shape and to release the internal stresses. Another investigation we performed in the lab scale is the investigation of the viscosity depending on the temperature of the fiber reinforced polymer composite. And in order to be able to rate the thermoformability of the 3R composite material, we compared it to a carbon fiber reinforced polyamide 6,6 material, and with this material we know that it's well thermoformable. As you can see, both materials show a drop in viscosity in the processing range, but also the viscosity of the 3R material is much higher compared to the thermoplastic material, and this states that the biggest challenge in the thermoforming of the 3R composite materials is the high viscosity of the 3R resin. And also this result leads to the assumption that the material need time to adapt the shape and to close the eliminations which can occur during thermoforming. Okay, let's go to a thermoforming process with a higher degree of deformation. Here, a little thermoforming test rig was developed, and the objective was to improve the thermoforming results by, for example, heated consolidation. In this investigation setup, the specimens were placed in an IR heater field to achieve the processing temperature. Then the specimens were transported automatically to the mold and were thermoformed. Here, two processing approaches were investigated. On the one hand side, the thermoforming with a cool tool with a tool temperature of approximately 25 degrees. And the second thermoforming approach was a tempered tool with approximately 210 degrees, so at the forming temperature of the 3R material when it arrives in the mold. The results are summarized in the table, and as you can see, when you thermoform the 3R specimens with a fiber reinforcement in a cool tool, the spring back clearly occurs, and also the number and size of the eliminations in a forming rodi are pretty big. Also, no ply sliding was achieved. On the other hand, when you use a tempered tool, no spring back occurred after the holding time, and also the size and the number of the eliminations was reduced, but also here no ply sliding occurred. In order to improve these results, a further consolidation concept investigated was the use of a high temperature resistant silicon layer in the mold. Here you can see the difference between the thermoforming concepts. On the left hand side, consolidation with a heated tool without a silicon layer. On the right hand side, the consolidation when using a silicon layer. And you can clearly see that the quality of the thermoform part was improved massively, but it seems that the consolidation time and the consolidation pressure of 4 bars in this case was not sufficient to completely close all the delaminations. So in the next step, we adapted the experimental setup and apply higher consolidation pressures and also longer holding times. And this led to a further improvement of the specimen quality after thermoforming, as you can see in the specimen in the lower right side. And now, when taking a closer look to the specimens when they were thermoformed in a polished cut image, you can see that all delaminations were closed and only a few defects occur in the thermoformed part. A little issue here was that the path of the load-bearing fiber structure was distorted, and in order to improve this, we investigated also other input materials. So in this case, the 3R enduring pre-pregs. So here we use stacked single layers which are not bonded as an input material. And then they were also thermoformed in the same process. And here you can see a very nice path of the fiber reinforcement. Also, all voids are closed, and also a nice ply sliding occurred. In the next step, we upscaled the thermoforming approach to a nearly industrial scale processing. Here, a typical thermoforming process was used with an adapted tooling, here tempered tooling, and also concepts for the pressure homogenization in the mold. The flat laminate was preheated in an IR field, then automatically transported to the already heated mold. The mold was closed, the material was shaped and consolidated, and also cooled in the closed mold while applying the consolidation pressure, and then after the cooling the parts were demolded. How does this look in real life? I can show you here in the video. The material was heated in an IR field for 60 seconds, then transported to the mold, and then thermoformed pretty slow, here with a closing speed of 5 millimeters per second, and then, as already mentioned, consolidated and cooled in the mold. In order to prove that that the ply sliding took place, we used the approach that we drill some holes into the laminates right before thermoforming. And by the change of the geometry of the holes during the thermoforming, we can prove that the ply sliding took place. And now the question was, why do we here achieve a ply sliding but not in the V-shaped parts? And our finding is that the double-banded thermoforming ruddy benefit ply sliding in the part because of additional shear forces occurring during the forming process. And we also expect that after a further process and material optimization, thermoform parts are achieved which are ready for industrial application. Another thermoforming process is a continuous compression molding. Here we use stacked individual single EPP layers with an infinite length, and they are consolidated and shaped within a process. So the stack is put into the mold, pressure and temperature is applied, and after a feed of the material step by step through the mold, the final part geometry is achieved. And the biggest challenges in this process is to choose the right temperature at the right place along the forming tool, and also to achieve a homogeneous pressure distribution across the whole tooling length. And also, pretty big challenge is to the mold development to achieve a suitable mold geometry to achieve defect-free parts. A special issue here is that in the processing of the CCM, an additional EPP layer was placed in the input material in order to achieve different thicknesses in the part, for example, for local reinforcement. The manufactured demonstrator parts you can see in the image, and the polished cut image show that the consolidation in the part is very good, and also a different thickness is achieved in the part by the additional EPP layer. A springback of the part was also not detectable, and we here clearly can state that the TRL5 was achieved, and after a further process and material improvement, we also expect that this process and material is suitable for industrial applications. And now I'm at the end of my presentation. To summarize all the statements is that the Whitmeyers can combine the advantages of the thermosets and thermoplastic materials, and the high polymer viscosity is the biggest challenge in the 3R thermoforming. So special consolidation concepts are necessary. Heated thermoforming tool is recommended, and also slow thermoforming speeds are required. The thermoformability in a discontinuous and continuous compression molding process have been achieved, and also the TRL5 is achieved. So now I'm at the end of my presentation. Thank you very much for your attention. If you have any questions, feel free to ask.
Thank you very much, Stefan.
Thank you.
Okay, thank you. Yeah. Okay, as in the other presentation, maybe we can leave the questions for the coffee and go ahead with the presentation of Hasman, if it is possible. I don't know if we have solved the audio problems. Hello, Philippe? No. Yeah, no, okay. Good. Okay, good morning, Philippe. I already introduced you, so I think we can go with your presentation. Thank you very much for attending the workshop and for this presentation. So.
Okay, thank you very much. And I am really sorry not to be able to be present with you today. So, as I said before, I'm really sorry not to be able to be with you this morning. I'm glad to be here with you to present you the Huntsman, let's say, approach for sustainable aerospace resins. As it was mentioned rapidly during the presentation, I had the chance to listen just before. We are a supplier of epoxy resins to the aerospace steels, prepreggers, different formulators, and what we try to think about is how should we bring more sustainability into the aerospace resins, and this is what I want to explain today. So it's not only in aerospace, but we receive more and more requests for different industries about sustainability in terms of what are you doing, what are your plan, what is your roadmap. So in the aerospace, it's the same. We had discussion with different OEMs, different tiers, and it's always the same question: what is possible to do in order to reduce the environmental footprint of the overall industry, and for us in particular for the resins, the matrix of the composites, or for the adhesives also. Today, what is important to understand is that all the aerospace resins are produced only with qualified raw materials. So we don't have as it is the case for other, let's say, resins for other industries. We don't have this the raw material flexibility. Raw material flexibility does not mean that we are doing what we want in not a structured way, but that we have several raw materials qualified, and that also the qualification of new ones is more straightforward than in aerospace. So what is the current situation at Huntsman in terms of sustainability, and more I will focus now on the bio resin, because very often this is what we are asked for. It's what is the bio content of your resin, so what is possible. So the setup at Huntsman is the following one. I hope you can see my my mouse here. So on the top, you can see the manufacturing setup for the industrial epoxy resins. So we introduced the use, for example, of bio-epichlorohydrin, which is one of the main components for the synthesis of epoxy, more than 10 years ago. But we introduced this mainly for markets such as sport, electrical insulations, or other like this. And in that case, our EP supplier, they are manufacturing epichlorohydrin from two routes, the fossil one and the bio one. So the first one based on polypropylene, the other one based on glycerol, and they are going through, let's say, a common synthesis process or line. And then we are delivered at Huntsman with a mix of fossil and bio-based epichlorohydrin. Then we manufacture different epoxy resins on dedicated industrial lines, and we can produce this kind of resins with this kind of typical bio content. The problem we have is today that we have the information retrospectively. I mean, we are informed at the end of each year about what was the average of the bio content in the EP we bought, and this is due to the fact that the bio EP is governed by the bio feedstock availability on the market. So, but since now 4 or 5 years, we are about 50% plus or minus 1%. This is why we can say that typically we have this kind of bio content in our different resins for industrial application. For aerospace, as I said before, it's only based on the propylene route, and we are today manufacturing different kind of epoxy resins. For them, the content of biocarbon is 0. What we have done is we have started to look at what the LCA, the life cycle analysis of our resins, and one of the main conclusions was, as it is seen on this graph, that the main contribution of to the global warming potential is coming from the raw materials. This is why we decided to focus on raw materials and to try to find a solution on it. So on this graph, you can see that the green part is more, we can say these are our emissions, these are the energies and utilities we use for the production. So this is what is called the scope 1 in general. Our emissions are significant, but not the main part. So the focused, so even if we still work on this, on our plants, I will now talk to you about the raw material. So there are several routes possible to introduce bio feedstock, with having in mind that the ultimate goal is to reduce the environmental impact. So first, I mentioned the bio EP. 50% bio EP it's what we do today. It's feasible. Going to 100% bio EP, it's feasible also. There are suppliers of 100% bio glycerol-based EP. For biosubstrate, it's not the same story. So biosubstrates are the molecules that we will epoxidize to make the epoxy resin. So it can be bisphenol A, this can be bisphenol F, phenol, or methylene also, paraminophenol, metaminophenol. So these are the main substrates. We are also doing also reactive diluents, but this is not possible. These products are, especially for the substrates for the main resins, they are not available today and not in the short term as a bio-based, a real bio-based. For reactive diluents, some exist, some not. what is the consequence? There is a limitation of the bio content in the final epoxy resins. This is why today on the market we can find the resins with about 20–30% of biocarbon. There is another problem mentioned with this 100% bio-EP would be, and also even the 50 would be in case of aerospace, the requalification because of change of source of supply. There is another route that we decided to investigate, which is in fact the mass balance concept. And we believe this is the short to medium term, the most efficient solution. So it will be, we will not speak about the bio content, but bio attribution, so bio attributed raw materials. One of the main advantage is that there will be no limitation, if I can say. Of course, there's a limitation when everything is bio-attributed. You cannot go further, but it's you are not limited to the only what is coming from the bio-EP. So the mass balance concept is just this slide is to explain that it's a similar concept as when you are buying green energy at home. The energy is produced from non-renewable energy or renewable one, which is, for example, wind or solar or water. And then it is distributed, but you don't know when you are at home if the electrons that are making your lamp or different house equipment functioning are coming from the renewable energy or from the non-renewable ones. But you paid for and you have a contract that guarantee that you contributed to saving fossil resources. So in the case of biomass balance concept for chemicals, this is the same. We will mix fossil or biomass at some point in the manufacturing chain. Then we will produce our products, and in fact, we will segregate in the books what we are doing with the raw materials which are certified as being bio-based. And then we are selling our resins, which some of them can be bio-attributed, some can be non-bio-attributed, and we sell them to our customers and then to the aerospace industry with the effect to reduce the CO2 emissions. There are today 3 major official certification schemes for chemicals. There are several others, but the 3 main ones are those which are mentioned here. The ISCC with the ISCC Plus scheme, the RSB, and the Red Cert with the Red Cert 2. We decided to go with Red Cert 2 because as you understood, we use different raw materials, and we cannot force our suppliers to all use the same certification scheme. And for example, ISCC or RSB, they do not accept the others. So they want everything to be ISCC certified or everything being RSB certified. In the case of Red Cert, they accept the other schemes. So it means that, for instance, to produce multifunctional epoxy MY721 or BLR, sorry for the noise with the fire brigade. So I said to produce our 2 resins, we can, for example, use the methylene dianiline MDA, which is Red Cert 2 certified, together with the epichlorohydrin, which is RSB certified, and then have at the end a product which is Red Cert 2 certified, and the same for a standard basic liquid resin. Red Cert in 2008, it's an official and recognized scheme, and it was developed first for the fuel application, and then in 2018 there has been an extension for the chemical industry. Today the situation is that we identified our main raw materials available as certified. For example, as I said, the epichlorohydrin, RSB, MDA, Red Cert 2, phenol, or bisphenol A, ISCC. And with those 4 types of raw materials, we can cover all, more or less all our epoxy resins and get them certified as bio-attributed, and then, of course, propose it to the formulators, prepackers, and OEMs. There is something important now linked to aerospace is that, okay, so the mass balance concept I explained, so circular or bio-based feedstock mixed with fossil feedstock, and then segregate in bookkeeping, and then producing, and then attributing the mass balance units. So in fact, when we buy bio-attributed raw materials, we can then attribute those credits, so those mass balance units, to different products, and then we can produce different kind of products, up to 100% bio-attributed, but some will be not bio-attributed. And there is another concept. It's that the physical plant where we produce is, let's say, the limit of the exercise. It means that in this plant, if we have let's say, two buildings where we produce in one building the resins for, in this example, for skis, and here resins for aerospace, we have, for today, as you understood, different physically separated tanks. So tank for AP industrial resins and tank for AP aerospace. Also tank for the precursors. And the cross-allocation concept allows to allocate the credit from one from one application to another. It means that if we buy raw materials to make those resins, industrial resins, we can allocate the credit to the other resins, the aerospace, because it's technically possible, it's the same molecule. So what does it mean? It means that, for example, if we produce resins with raw material flexibility, for example, bisphenol A plus epichlorohydrin, this one being certified, we have the choice not to sell this resin as certified, but to use the credits. For example, if I take the example of the Araldite M-White 721, which is the TGMDA resin, we have the possibility to combine the credits coming from the MDA that we will buy to the credits that we got from RSB for the industrial epoxy, but to allocate them to the TGMDA and have then 100% bio-attributed resin. So in fact, the credits are used based on, let's say, a calculation which is based on the lower heating value, which is in fact the calorific energy of each chemical. I will not enter in the explanation of how the calculations are made, but for example, if we say methane as is the reference is 50,000 kilojoule per kilo. Epichlorohydrin is about 16. G-bar or TGMDA, they are both around 30,000. So then there are calculations to make sure that at the end the balance is not negative. I mean that we will not sell more than of our products in terms of mass balance units than we bought at the beginning. It's possible, another example, for the TGPAP. So the para-aminophenol is not available today as certified. In that case, we could allocate the credits from epichlorohydrin and get, in that case, TGPAP up to 50% bio-attributed. So the benefit is that there will be no change in the reality, in the production, no change in raw materials, no supplier change, no grade for the aerospace resin. There will be no change in the plants or the processes at supplier and also in our plants. And the specification for the raw materials here will be the same. And also our specification will be the same. So there will be no need for requalification. It's in fact the mass balance concept happens only at the certificate level, and everything is validated, audited on a yearly basis in each plant by a third party, which is let's say doing it I would say each plant, each year, multiple plants, they are very used to this. What would be the implication in terms of final benefit that we look for? They will allow a significant CO2 footprint reduction of our resins. And here you have two examples of what we calculated. Today, if we would use to make a standard liquid epoxy, I would say bisphenol A based, for instance, the carbon footprint, the global warming potential is 5.4 kilo for our resins made in Switzerland with 100% fossil raw material. It will be 5.4. If we implement the mass balance certification process, we would reduce by more than 70% the GWP. In the case of this Alaitz 721, the TGMDA, which is one of the main resin used for composites in the aerospace industry, the reduction would be around 60%. So this is what we can achieve if we focus only on the raw materials. Of course, we are also working on our own emissions with our ambitions. We have, as a lot of other companies, we have the ambitions to be carbon neutral in 2050. But we will not wait until that time. We are already working on this, for instance, by reducing our consumption of natural gas. And how is it done? It's to connecting the plant to the incineration plant of the city. So these are different kind of projects like this. There will be a possibility also, because one thing that is important to say is that going to certified raw materials will have a cost for us, and this cost we cannot absorb only everything at Huntsman. It should be something, from my point of view, shared in the value chain. But if cost is the blocker, at least until a certain time, there is a possibility also to go for several levels of bioattribution by involving only the epichlorhydrin, only the substrate, both two different. So this is a question that will have to be answered by the let's say the value chain, the different actors in the value chain. In summary, what are the benefits of the mass balance concept? So the first one, because we are not looking for introducing a bio for the sake of introducing bio. The goal is really to reduce the carbon footprint. So there will be a direct impact on the life cycle. There will be no need for requalification of raw materials or for requalification of the resins for aerospace industry. And there will be possibility to claim in the value chain about the fossil saving. So I will give you just after an example of what we could claim. And here it's an example of certificate. So either the claim that is recommended by Red Cert is, for example, this product that will be bought or will be sold by us is a resource-saving product, and depending on the product, depending on the quality we want to sell, X%, so will have to be defined, of the fossil feedstocks were replaced by biomass. Or another claim will be the replacement of fossil feedstock led to the greenhouse gas emission reduction by X ton of CO2 per ton of product. So this is also these are two types of claims that can be done along the value chain. So from our suppliers to Huntsman to the formulators, and formulators to the end users. So it's the last slide of my presentation. I wanted to be quite let's say fast because I understood you are also late in the agenda. But I am ready to answer questions if there are any questions now. I hope it was clear enough, not too fast. Let me know. Thanks for your attention.
Thank you, Christophe. Okay, thank you again. And yes, as you are not here, we can have time for a couple of questions if there are any questions.
Yep. If questions come later, perhaps you can give my email address to the audience. If anybody has questions, don't hesitate to come.
Okay. No, I think yeah, you have been very clear, and it has been a very clear presentation, because we do not have questions here. So thank you very much again for being this effort.
Just the last comment from my side is that our ambition is to have this kind of certified raw materials available for the beginning of 2023.
Okay. Okay.
We have started the certification process.
Okay. Okay. Thank you very much, and yeah, have a nice day. And we say goodbye to you from here.
Yeah.
Okay. Bye. Okay, so the first session is finished with this presentation. So now it's time for coffee. We have half an hour, and we will come back at quarter past 11.
The first presentation will be done by Juan Pedro Berro, which is a partner of the AIRPOXY consortium. Juan Pedro is degree in aerospace engineering and master R&D. He also received his PhD on the development and numerical implementation of a wound composite damage model and burst prediction of a composite overwrapped pressure vessel. Juan Pedro joined Altair France in 2013 as a R&D engineer, leading several collaborative projects focused on composites modeling and optimization. In 2017, he joined the Altair Radios validation team as Radios composite and manufacturing specialist. Now, he is leading the French R&D and PD project team, including 13 engineers, focusing on topics where the converge of data, simulation, and HPC are races. Juan Pedro, I give you the floor.
Okay, thank you, Nerea. Hello all. So let's talk about virtual things now. This presentation is about the work we did in mainly work package 2 and 5, focusing on thermoforming. Okay, so I have only 4 slides with equations, and then we will see some funny things. I will start explaining the material model we developed for the 3-year resin composite developed in AIRPOXY. So fabric resins, how we calibrate this material, just very fast, and then all the simulations we did concerning demonstrators. I classify into 2 levels, semi-structures, so the first ones, and then the industrial demonstrator that you will see later. Okay, so just a little summary. Why we developed something new here? Because this resin is not the same resin we used to simulate, okay, in our site at least. Normally for thermoforming, 99% is thermoplastics, okay, and the material models for thermoplastic we know quite well. But this new resin is something strange. It's like a thermoset, like a thermoplastic. We don't know how, what we need to put inside in a numerical way. So we try to develop a fully new material model, okay, in our software. We use Altair Radios. This is an explicit finite element code. Because for thermoforming, we need to move to explicit, it's too complex. And the idea was to develop in one side the reinforcement, in the other side the resins. For the reinforcement, we decided to choose an hypoelastic material model, which is really clean and beautiful from a mathematical point of view. And the idea here is to be able to track how the fibers in a fabric or even in a directional composite moves, rotates during the process. Okay, so all the work here is how to use metrics, mathematical metrics, and here is the gradient deformation tensor to move from what the finite element code sees, the element with his elemental reference system, to the local fiber systems, okay? In order to deduce the deformations for the fiber 1, deformations for the fiber 2, which is the shear angle between both. So all the work here was to how to move from the finite element basis to the local basis in fiber 1 and fiber 2. So a lot of different tensor computations and so that is okay. And then when we are in the fibers, we can implement the behavior that we want, okay? And during this project, we put this kind of behavior. So we have a dissymmetry in tension compression in order to capture the effect of waving in fibers. So when we pull, it becomes straight, and then we retrieve the stiffness. And when we are in compression, we lost a lot of stiffness because the fibers enter in compression, the wave increase, and so on. The other thing we did is to add a sort of plateau at the end in order to localize the risk of fiber rupture. Maybe in AIRPOXY 2 we will implement a real damage model, I don't know, but it would be nice. But at least this kind of solution is enough to localize risky zones during the simulation. How we implemented that? So we use the standard for those that use simulation software, finite element software. We use an user material framework. 80% of operations did inside is just to make these changes between elemental reference system and local basis for fibers, and then we actualize the stresses. We sent to the code, and we did that a million of times, depending of the duration of the simulation. So this is for the reinforcement, and then we need to put something for the resin. This is a philosophical question for people doing manufacturing thermoforming simulation. There are two ways. So the first one, which is the one I like, is use viscoelasticity. And the other is using an elastoplastic model for the resin. Both needs to be thermal dependent. So for the first one, we developed a Maxwell general model with at least 4 branches, and we introduced the thermal dependency in the viscous modulus and the relaxation time. So we saw in the presentation of Alaitz the curves. Okay, so we put the same in the model, and it's okay. For the elastoplastic behavior, it's just something standard, Johnson-Cook with a strain rate dependency, or thermal dependency. So this is for the resin, and at the end we addition the stresses coming from the resin and the stresses coming from the reinforcements, the fibers. It's sample, but it works. For the material calibration, it's composite. So we need tensile test for the direction 0 and 19, bending test, shear test or bias test, and all of these at different temperatures and different strain rates. So it's quite hard to calibrate this kind of materials. But at the end, we achieve something that behaves really, the behavior is really close to the real one for fabrics, for unidirectional, and so on. Because we needed that to simulate the structure that I will show later. So, okay, we have the material, we have the implementation that works in radius. So let's try with a sort of semi-structure. So structure that are a little bit more sample than the industrial demonstrator. So the first one we tried is the spherocylinder. Here we compare, for example, the viscoelastic resin and the elastoplastic one, some different ways to model the laminate. And the conclusion is that elastoplastic or viscoelastic works quite fine. We detect defects. This is our goal here. We want to detect defects and guide the design of the manufacturing process. And you can see on the other side the shear angle. The other structure is the hemispherical test. So we did two okay, with different thicknesses. And here, the specificity of this model is that this is a pre-consolidated laminate, so each ply is linked to the others. And we needed to implement something to represent that. So we put a connection between plies, because each ply is modeled explicitly here. And we needed to develop, again, another material model, which is a cohesive one, to take into account the delaminations that Stefan, for example, showed before. And we performed the simulation, putting the correct temperature in the plate, in the tools, and so on. This was a blind test, this one. And we can see all the massive delaminations that are coming during the forming process. This is a heavy simulation anyway. And if we compare with the real sample, we see that we are quite close. Okay, we can localize the wrinkles, external wrinkles, internal ones, and if you see in the boundary of the sample, we see more or less the same patterns. Okay, and the interesting thing is that when we change the thickness, the patterns change. The way that the sample deforms during the manufacturing process change also, and we're able to capture that. So we were quite happy with these results, and we decided to move to the industrial demonstrators. So the first one is the longitudinal stiffness. This is an omega with section change in more or less in the middle, a little bit further, and we have two plies inserted on the center of the omega. Again, these are pre-consolidated, so we need to put, as you can see also. Oh, sorry. You can see in the here this cohesive element to represent this link between plies. And we have avoid region because we can't put something with this shape. So we are a little bit conservative because we're going to see that something happens there. So during the manufacturing process, we see, this is almost clear, something happening here. This is the change, the thickness change. And this almost wrinkle at the end with the consolidation disappears. Okay, disappears in the simulation. If we compare with the reality, we see that there is a wrinkle anyway, external one. So we consider that maybe we need to go further in the mesh size. So use a mesh much smaller in order to capture the shape of this defect. But the problem is that if we decrease the mesh size, we increase a lot the computation times, and it becomes really hard to use this to guide the manufacturing process, because this is before the manufacturing process. If we spend more time doing that than doing trials, why we do simulation? It's not maybe to limit the materials that we use. Anyway. And then also with this approach, the interesting thing is that we can explore the delamination at the end of the manufacturing process, but before consolidation. Okay, so we can see here that in this zone we have a lot of delamination, but also in the outer radius and even in the middle, which is the zone where Stefan showed before. There is a lot of transverse shear in the through the thickness, and at the end of the process, it creates a sort of delamination there. The other demonstrator is the leading edge. This is the most challenging one from the beginning. We spent a lot of time with this. I show here the different points that we treat with this demonstrator. So, for example, we started with a symmetrical web, so with thermoform the symmetrical, and then we create the whole web. We study the cut's influence on the flat shape. Maybe not to have a square flat shape, but something different. Blank holders, which one? How we put the blank holders? Piloted by forces, by displacements? We don't know. We didn't know at that time. We explored the options to put some springs to add tension in the flat shape, and then we move step by step to more close to the real manufacturing process simulation in order to guide and to decide what to do. So here an example of how the cut in the flat shape influence the wrinkles in the leading edge. So just for your information, here the tip of the web is the critical area in these demonstrators. There is always something happening there. And the idea is cutting the flat shape. Maybe we can influence the way the wrinkles appear or make it appear outer the functional zone. And the best trial here was to make a cut in 45 degrees because it creates a sort of line here, but less wrinkles. This is one exploration we did. Other thing it was the spring analysis. So the idea was to put some springs. We did that in another European project, and numerically perform and design of experiments and optimize a little bit what we get in order to optimize the stiffness of the springs to limit or avoid the wrinkles. Using a little bit of machine learning also, so we get some fun doing so. And the last trials was how perform the manufacturing process with blank holders. Okay, we studied if we put a blank holder which is fixed, which gap, if not, which force we need, how many steps, 1 step, 2 steps. Anyway, we made some simulations, a lot of simulations here, and the goal was, as always, look at where the wrinkles appear and if it is far away from the functional zone. This is our goal here. Okay, so with each simulations we provide some information, and AIRE took that and improved the manufacturing process. So let's show the final trials that we did and compare with the real test. So this is with EPP. So each ply can slide, and we can compare, for example, in that side, different stages of the process. We have more or less the same kinematics, but also we're able to predict more or less the wrinkles and the area where the wrinkles appears. Okay, and it's complex, like as a simulation. So I was super happy to get that, because normally this is not the case. There is always some defects that appear and you don't know why. But in this case, was quite good. And then we moved to the final trial with an aluminum sheet on the bottom, and again with the blank holder and these lateral extensions, we get something which is quite close to the final part before consolidation again. We perform also the RTM, so pre-consolidated with the connect cohesive elements to capture also the lamination. And here in the experimental part, okay, 5 minutes. It's okay. It was quite surprising because the RTM in this case was better. We performed the simulation, and okay, it's better. We get less wrinkles. For example, in the flat zone, we have nothing. Okay, it's just on the tip. There are always something there, but really concentrated in one line, more or less the same that we get in the real part. Okay, so the last simulation we did with the lateral extensions, again with the RTM. So you can see the delaminations on the left. 2 main zones of wrinkles in the external part of the web, and in the internal part again we see a lot of wrinkles around the tip, but even a little bit displaced on the right. So as a first implementation of this kind of material laws, which are thermal dependent, with cohesive, with contact, and a lot of things, we achieve a quite successful prediction of defects, and we help AIRE Composite to improve or to do less trials anyway, in order to achieve a successful manufacturing process. And I think that is all. Okay, the conclusion. So well, I think that I did. So we developed a new material model, a new method, in fact, because these cohesive elements for thermoforming, nobody does this, but we need it for the epoxy resin. We tried with this semi-structure with very good results. We tried with industrial parts, and we get again successful results if we take the simulation to guide the manufacturing process. It's a sort of pre-design phase. To be quantitative, I think that we need to work more because it's super complex, but I think we are in good shape to continue to improve this. And that is all from my side. Thank you very much.
Thank you, Juan Pedro. I think that we have time for 1 or 2 questions. Any questions?
If not, I will leave after the lunch. So during the lunch, if you have some questions, I will be glad to answer.
I have a question. Okay, so my question is, which are the next steps to bring these simulation tools that you have developed in the project to reach the market? Is the ready or?
It's ready. We were waiting for the correlations that we did in order to implement that in the commercial code. So because today is something external that we develop and we use. Everybody can use if I provide the good piece of code. But the next step is to implement in the code, and a customer of HyperWorks, so the Alter software, who will be able to use this.
Okay, it's good.
It's
Thank
good.
you. Thank you, Juan Pedro.
Thank you, Nerea.
Okay, so let's continue with the session. The second presentation was going to be made by José Luis León. He's the managing director of CIDETEC, but he was unable to attend the workshop due to a last-minute unforeseen event. So Diego Calderón will present the talk instead. CIDETEC is a key reference providing the market with complete solutions in the field of autoclave advanced composites. And well, Diego is going to give us CIDETEC's vision of trends in these technologies. I have to say also that well, CIDETEC has been a partner of the project, so we will see Diego again in the presentation. So Diego is a material engineer, and he has 21 years of experience working for CIDETEC, where he holds different positions. Structural Analysis Department Manager, Head of Materials Review Board at CIDETEC for Airbus Defense and Space Projects, Head of Materials and Processes Department, and Technical Coordinator for R&D projects. So I give you the floor.
Well, thank you for coming. As Nerea said, this presentation was supposed to do by José Luis León, our boss, that maybe is more known in this sector than me, but unfortunately he couldn't come and I will do the presentation. But I think the message will be the same, and fortunately for me, I think it will be very similar to ones that we have already seen. For example, I think it's very in line with José Sánchez said and explained. So I think more or less all the industry is more or less in line. So well, we will see. Well, this is more or less what I will going to talk about. I will make a small introduction. I will focus in materials, then in processes, and then a small conclusion and some reflections. First, who we are. We are CIDETEC. We are a company that works only in autoclave processes. It's our idea to work in RTM, sometimes in infusion, but maybe RTM is maybe not, it's our technology. We are not so many people. We are about 100 employees, but we do a lot of things. And we do all the cycle of development, from design analysis, design of the tooling, manufacturing, quality inspection, and so on. So we can do the complex cycle of the development and manufacturing of the part. We are in Vitoria, in Miñano, very near from here. And then we have another plant in Cádiz, in the south of Spain, very near to Airbus facilities. Well, I was told to talk about the emerging trends, specifically in RTM. So with a quick brainstorming, these are the topics that I think everybody has in mind. Recyclability, we have talked about it, and we will talk later about it. Bio-based materials, low energy consumption, reduced carbon free, high rate productions, a lot of things. Okay, maybe more focus in RTM is the key, or the strong point of the technology is to ability to have some high complexity geometries to achieve a good level of integration. And the last trends, and one of the points that we have worked a lot during AIRPOXY project, is to improve the toughness of the epoxy resin or the thermoset resin, and at the end to have a high performance materials. So, well, I think more or less these are the topics, and we only have 20 minutes, so it's impossible to talk about this. But what is more important, and the key of everything, is to reduce costs. Jose told about this. All of this is quite nice, is challenging, but it will be we will not see it in any plane if we don't reduce we got a reduce of cost between the baseline or the solutions that we have right now. If we go to the materials, maybe you all know this kind of materials, non-cream fabrics, that some constructions that are cheaper, that have a good mechanical performances, but they are not suitable for complex parts that are the key, as I said, in RTM. Then we can have tailor-made fabrics. We are used to work also with high modulus fibers, but again, it's so complicated to certificate any material, although it can be fantastic. So, or we reduce the test to certificate these materials, or we will work with the same fabric and the same resin for other 25 or 40 years. That Nerea said, I has been working for 20 years in CIDETEC, and I only know one resin reference for aeronautics and 2 carbon fibers. So I have worked in a lot of projects in development, and we still go for the same materials in the new projects. So something is not working here. But it's not our responsibility. We are just a tier 2. But well, the only thing we can do is to express our opinion, and hope if somebody has to take that controlled risk. That was the key, I think. Then we are trying to get in new projects with some people from here, also with recycled fibers, bio-based fibers. We know, and we are working also with 3D printing fibers, different ways. But again, and I will repeat it several times during today, it must reduce the cost. If not, you go to the procurement department with Airbus, and you will be discarded as an option in any trade-off that you can do it. So then regarding the resins, just a quick review. We used to work with epoxies. As I said, as the only one resin that is certified, we all know that it's very fragile. We have some problems with the toughness. There are some solutions that we have worked during the project to try to improve this by adding some thermoplastic base. It's not very innovative, but it's something that it must be continue working. And we got some nice results in some properties. Then again, the recyclability is a key. I mark in yellow reparability because was our main interest in the project, and you will see later in the next presentation the results and why for us it can be very, very important. And then another point of improvement in the thermosets is to get a fast curing. We have some people here that come from automotive sector and know that this can be achieved, but again, you can have a fantastic resin, but it must be certified. It must be suitable to work in certain conditions, but it must be cheaper again. Okay. Then we have BMI. It's a resin that has been used sometimes. It has a very high temperature. Also, it has a higher viscosity. It's not so good to inject. But well, we have done some things, and there are some OEMs that are working with it, and it can be a possibility, but it will be like 2 or 3 times more expensive than an epoxy. So again, if maybe a metal solution is better, we don't know. You have to do it. And then thermoplastics. We don't work with thermoplastics, but we know that PIC is a possibility. It has a very high TG. It can be easily or more easily recyclable. But the drawback is that the temperature process is very high, so the process, again, is very expensive. And we, again, have the same problem. So all these things are fantastic, and we are working for trying to achieve these objectives, but if we don't reduce the cost, we don't have a solution. I think that's the message, okay? But I want to show some of the new things that we are working for the last years. Well, this it's a trend in the RTM in the general sector. We can have robots to do the placement of the dry fibers in 3D sections, but that robot that I put in that image is quite expensive. Again, you have to do a very high rate production in order to save money with that kind of machine. Another option is to put the layers in 2D in a plane shape and then do a thermoforming or a hot forming in this case with the dry fibers. In this case, some examples we have working. The first one is a 3D printed tooling with a Ultem 1010 resin that can withstand up to 210 degrees, so very high temperature that cannot be withstand with an epoxy or a normal epoxy resin. And that was another development project that we had. And the other solution is to have a epoxy resin plate that you can do then a machining in order to get, in that case, a wingtip shape. So the process will be to do a 2D deposition of the fiber and then take that layup, let's say, to the molding, to the mold, do a hot forming with a silicone membrane and apply heat. Depending on the binder or the bale, in this case it should be a thermoplastic bale, as I said before. You can then have a stiff preform that you can then take to an injection mold in order to save time. In order to save time, save operations, save money. That's the way we are working at CIDETEC. RTM, as you all know, is a very manual technology, and the only way to try to be competitive against other technologies is to reduce cost, again, during the manufacturing process. So we are trying to automate the process. Also, our geometries are quite complex, and it's not easy to do this automation. Okay. Then regarding the tooling, some new things. I think we have people from ITIP here. We are working with them to manufacture toolings with additive manufacturing. In this case, it's with steel. The technology is called BAM, it's wire and arc additive manufacturing. So this case is one of our last developments. It's the part that you saw before is a wingtip. So the mold is generated in 3D printing with steel, and then it's machined in a normal way, let's say. And this allows you to make complex toolings, saving some cost with the material, because you are not, you don't have a big raw rectangle, let's say, or cube to do the machining, but you are only using the material that you are going to need. And then, for example, you can have a complex oil conduction inside the mold that in some companies is not allowed, but in some others, yes. So I think it can be a good way forward. Again, the oil heated tooling, you can have very fast heating, up to 5 degrees per minute. That it's the maximum that we are allowed in aeronautics. You can save energy, you can save in this way some money, but you can have the problem of the contamination with oil. That is one of the drawbacks, and the reason in some cases it's not allowed to use this technology. But well, there are ways to try to reduce the consumption of energy that in these last months it's a nightmare for us. Okay, and well, I think this is the key of all the RTM. The design. To design the parts focused to the process. We have seen for last years, or in fact all my career, when we receive the drawing or the model of the part that we must manufacture, that is, it's what we call a carbonization, that it's a metal part that the customer wanted in carbon. And well, the numbers don't fit. If you want to have a good part, you have to design it thinking in the tooling that you are going to have and how you are going to do the molding, and think finally in the cost. So the other point is to promote the integration of parts. This is a part that is manufactured by Airbus in Getafe, if I'm not wrong, but the design was done together with Airbus and us. It's a part that it has a level of integration very, very high. But if you see the parts, it seems like a normal or standard metal carbon frame. So it can do it better. We know that we can do it better. And that is an example of a carbon fiber part made in only one shot. It's an air inlet, and it's a part that if you have to do it in metal, it will be difficult. So this is the point. You have to design from the beginning, knowing how you are going to receive how you are going to manufacture the part. So then, again, to reduce the cost, you have to have a good design. To have a good design means that the geometries must suit the technology, but then there are other things. There are the structural analysis that must be reasonable, let's say. Yesterday at the dinner, we talked about some examples. We manufacture leading edges with the integrated ribs. that is in the middle of on the slide. And due to the methods of analysis and the test and everything, we are manufacturing the same kind of part each year, or in each project, it's thicker. So we are going back. Why? Because in the finite element model, you see a red point that says that maybe you are going to have a problem. So we are increasing the thicknesses, we are increasing the materials, so it's completely crazy. So we have to have good engineers, we have to take some risk, we have to test, but in a reasonable way. We have to have reasonable quality requirements. I will put some examples in the next presentation, and we must think in manufacturing. For us, it's easy because we have the same in the same facilities. We have the office, we have the workshop, so we can see the parts. But I have been working in big companies sometimes, and I see that the designer haven't seen a layer of carbon fiber. How you are asking to that people to think in manufacturing? That's very complex. So I don't want to discourage every people here about this, but that's a way to do the things. But we must be clever. We must have a wide view of all the problems, and think about the final product and how you are going to reach to that product. Okay, and I think that is all from my side. If everybody's shy and don't have any questions, I will be happy to answer you. Okay.
Thank you, Diego. So I think that we have time for one question. Is there any question? Okay, I have one. So you speak about the cost. In which part of the value chain do you think that there is more room for cost reduction? Is in the design, the raw materials, the production process?
I think it's in production process.
Production
Yes,
process.
if you have the numbers in RTM, yes, because as I said, we are manufacturing complex parts that take a lot of time of process. So in percentage of the cost in materials and hours working, I think it's in process. So that's why you have to reduce the process by automating, but also thinking in the process from the beginning. You have to design a part that it will cost not 20 hours of manufacturing because you have to do this corner in that way. So you have to simplify the models, you have to simplify the geometries, and you will have a more simple manufacturing process, and you will save in that
so at
area.
the end, you have to work also in the design to improve the process.
Yes, that's the key.
Okay.
Also, any improvement in the cost of materials will be for sure
welcome.
appreciated.
Okay, thank you.
Okay.
Thank you, Diego.
Okay.
So the next talk is given by Thibault De Lumley from SONACA and Diego Calderón from CIDETEC. Both are partners of AIRPOXY project, and they will present the two use cases. I have already presented to Diego, and now I'm going to present Thibault. Thibault De Lumley has graduated and master's degree in engineering mechanics. He has more than 20 years of experience in the aerospace field as a material and process engineer. He first worked for Dassault Aviation as a materials and process engineer and research and technology project leader, and has been working for SONACA since 2008, where he is leading the material and process team for advanced composite structures development. He has been involved in many research and technology projects related to composite materials and process development, in particular in the frame of international programs. So when you want, you can start.
Thank you, Nerea. So I will stay here because there's the light from the door, which is not good for the camera. Is it working? Yes? Yeah.
Yes, no, yes.
Okay, so Diego and I will present you the two aeronautic use cases for which 3 air materials have been applied at component level. So after a short introduction where I will present you the 2 use cases, we will present the motivations and the background for why we selected these 2 use cases. And then we will present you the design of the demonstrator, the main manufacturing steps, and the results of the validation test before having conclusions. So we selected 2 use cases. One is a subcomponent representative of a fan cowl door, and the second one is a subcomponent representative of a slat, which is a movable wing leading edge, which extend during landing and takeoff to increase the lift of the aircraft. So please, Diego.
We are the responsible of the leading edge, the fan cowl demonstrator that you will see later in the showroom. So I will try to explain it quite fast because I think the best idea is that you check it later. But why did we select this? Because we are the manufacturers of the A320neo fan cowl transverse stiffeners that is shown in the picture. Is the part that we have with a higher rate. We have manufactured about 80 engines per month, and one of the key in this project is that we are not allowed to open any non-conformity because of any damage. For example, if we have a small fault, a foreign object about a depth of 0.5 millimeters and 2 millimeters per 2 millimeters, the part is scrap. That is absolutely crazy, again. But well, in the case of delaminations, if you have a delamination about 4 millimeters width and 50 millimeters length, the part is scrap. This part can be about 2,000 euro. So when we heard about the possibility to repair these parts, so it can be a solution in a part where you can have some scraps and you have a very high rate, so the number of scraps is higher. Then the structure has some bondings, and well, one of the points of the project was the bonding also. So for us, I think it was a perfect demonstrator. Okay. So in the design, we did the design of a simple geometry with a plain panel, longitudinal stiffener with some difficulties, with a different thickness in the head and in the walls and in the head. Sorry, a thicker head thickness, and in the foot and in the web a thinner one, and then that pan down or change in the height of the section that could be could be a challenge for the thermoforming. But I think we thought in that moment that it could be a good challenge in order to compete with other technologies, for example, the stamp of a metallic part. Okay, and then the transverse stiffener that will be subjective to the repair. Okay. Sorry, the thicknesses were and laminates were completely representative of the real parts, so to have the demonstrators as similar as the real parts as possible. A lot of people has been involved in this. We were responsible of the design. The longitudinal stiffener I didn't mention this. It was a RTM plain panel that then was thermoformed. So the flat laminate was injected by CIDETEC, and then the thermoforming was done by AIRE. The simulation that you all have already see about Alter, some adhesion tests that were performed by University of Ioannina, as well as the city inspection that we will say later. Some AS scan also, and the bonding was performed by us. The skin manufacturing and the transverse steel manufacturing was made by us, and all the 3R materials was done by CIDETEC. So regarding the manufacturing of RTM, the best point here is that it's quite easy. It's a standard RTM process. We can achieve a high volume of fiber, that is 58%, that is the standard one in Airbus right now. The only thing is that you must have a continuous steering in the pot of the resin. We have been working with a monocomponent. Other partners have been working in some other stages with a bicomponent, with the bicomponent version of the resin. But we wanted to do it in monocomponent, and the only thing is that you have to do a continuous steering of the pot. The injection is quite good, and we have any problem with that. Then, regarding the longitudinal stiffener, the RTM panel was, as I said, injected by CIDETEC without problems. And then the process of this continuous compression molding was developed by IVW, and then over the demonstrator was done by AIRE, with a pressure of 50 bars, a temperature of 215 degrees, and a holding time of 30 minutes. That's the parameters of the process. Then the bonding is an adhesive film. We did it in 2 steps. First, with a vacuum bag, the bonding of both stiffeners, and then with a small tooling, we applied a mechanical pressure to join both stiffeners to the skin panel. Parameters of the process: 150 degrees, a holding time or a pressure of 30 minutes, and we have the parts bonded. In order to validate the demonstrator, we performed some 3D scan in order to check the spring back that we had, that we measure. I think it was between 0.5 degrees and 1 degree, that it can be recovered with the pressure of the finger, so it's allowable. A geometrical validation, that was okay. We performed some microscopic inspection, doing some sections, and also with a CT scan, a technology that was performed by University of Ioannina, where we can see that the quality of the demonstrator is nearly perfect. Okay. And then, in order to validate the joint, there was some lap strap tests that were performed to do some comparisons with other reference materials, providing good results. So, from this point of view, that was okay. Again, then we did some micrographies. We see some porosity in the adhesive film. It's a point that we have to keep working to improve that. Although that presence of porosity, the mechanical properties were okay, but well, I think it will be solved in the future. And then some coupons for the lap strap test that we mentioned before. And then the key point for us, the repair. In this kind of geometries, the laminations occur mainly in the radius. Okay. So in this case, we didn't have a delamination in the manufacturing, so we had to create it. We performed an unfolding test, let's say that, and we applied so much pressure that we create a full delamination in all the web, and also we lost the geometry. The section was completely deformed. From an angle of 100 degrees, I think we reached nearly 120 degrees. But we designed a tooling, heated tooling, that we put here in a press in CIDETEC we applied the parameters that were developed by IVW in previous steps that were 20 bars and 210 degrees. We applied that pressure for 20 minutes and we recovered the shape, and the lamination was apparently, let's say, welded. So visually there was no delamination. For sure, we did an ultrasonic inspection where we saw that mainly all the delamination was disappeared. Also, it was completely, all the layers were completely debonded previously or delaminated. They were welded, and there are some small areas in the edges that we think that they are due to some edge effect that were not completely repaired, as we can see here. At the left, you can see how was the laminate before the repair, and then how is the laminate in a CT scan after the repair. So in some areas it's completely repaired, and in some other areas we have a small delamination that, well, we must improve, but I think that the result is impressive. Maybe you can see it later. Also, we don't have the microscope here, but we are quite happy with that result. Okay. Yeah.
Okay, so regarding the leading edge, this is a component that we have been produced at SONACA for more than 40 years. In the years 2000, we have developed a hybrid concept with metallic and composite, where the trailing edge was a composite multi-cells structures manufactured by RTM, and that resulted in serial production of slats for the A350. And in parallel, we have also launched a development of a full composite slat with the integration of the electrical de-icing system. As it was said by José Sánchez this morning, composite is even more relevant if we can add some functionalities. So we have followed within SONACA technology roadmap with a step-by-step approach towards more integration. So why integration? Main advantages are the weight reduction by removing joints, also cost reduction by reducing the number of manufacturing steps, allowing also for high rate production, and also it allows for improvement of the general performance related to rivetless concept, such as the improvement of the natural laminar flow that helps to increase the aerodynamic performance, and also it helps to it makes easier the integration of a de-icing system into the structure. But we do have some disadvantages of integrated design. For example, we really need to control the process-induced distortion, since any deviation cannot be rectified with integrated design. Tools are more complex with that kind of integrated design, and we might have also some limitations on the part size. And repair is also a key thing with integrated design if we want to avoid scrapping the whole component. So within AIRPOXY, we have selected a less integrated design, but still with a rivetless concept. So the nose skin is made of conventional epoxy materials. We have a metallic sheet on the external side as a protection against erosion, and we have a 3-air resin film at the inner surface of the skin where the webs should be welded afterwards. So the nose was co-cured by SQRTM. The webs are made of 3-air composite laminate that are thermoformed. So each webs are made of 2 C-shaped profile that are welded together and welded to the skin using conduction welding. So here you have details of the joint. Yeah, with the nose skin composite no skin with the 3-air film co-cured to the skin. We have the webs made of 3-air composite laminate, and then at the welding stage, we added a 3-air film, which is also pre-cured, in order to improve the contact between the two parts. So the key features of that design was the use of multi-materials, the surface functionalization with the 3-air film co-cured by SQRTM, and also the complex geometry. We have a double curvature of the webs, which was thermoformed. So in terms of work sharing, lots of partners have contributed to the demonstrator. So the design was performed by SONACA. All 3 materials was prepared and supplied by CIDETEC. For the skin, CoExpert manufactured the SQRTM mold and SONACA manufactured the skin. For the webs, CIDETEC prepared and supplied the flat 3-air laminate and the noodles for the T-joint. Air Composite was responsible of the webs, thermoforming, and Alter performed thermoforming simulation. And the web to skin welding was performed by Air Composite. And the validation test performed by SONACA. So the skin was manufactured by SQRTM. SQRTM is a closed mold process that uses prepreg, which is placed into a closed mold, and the pressure on the prepreg is applied by injected a resin into the mold. And the resin we inject is the same as the prepreg resin. So the 3-air film that was inserted in the layup and co-cured was pre-cured to a degree of cure of about 48% in order to limit the flow of the resin during the SQRTM curing, but guaranteeing a good adhesion between the film and the conventional prepreg. So in total, we manufactured 4 skins, and we get a very good repeatability of the skin quality and a very good thickness control of the co-cured 3-air film. So for the webs thermoforming, we used the same process as it was used for the stiffness of the fan cowl, and all the details of the steps have been presented by Stefan in his presentation regarding thermoforming. So we had a series of parameters to optimize for the webs, and to do that we used both simulation as presented by Juan Pedro previously, and you'd seen that there was a good correlation between simulation and the experimental results. But we also had to do a large number of trials, first to validate the simulation and to define the best strategy. So here, for example, you have results we obtain using enduring prepreg, which are pre-cured plies stacked together, but with no pre-consolidation. And the results of thermoforming starting from a pre-consolidated 3-air laminate. And here you see that the best results was obtained from the pre-consolidated flat laminate. So here you you don't have sound, but okay, you can see the process of thermoforming. So you can see that, yeah, here we had a good control of the sliding of the composite and its cold plate into the tools. So we were quite happy with the process. In terms of results, we successfully demonstrated that the 3-air flat laminate was thermoformable, but however, it was difficult to achieve full consolidation. And the thermoforming was very sensitive to the initial blank trimming and alignment in the tools, and we could not get rid of the wrinkles in the tip of the nose as it was shown by simulation. But these issues is not very related to the 3M material itself, but probably to the geometric complexity of the webs, which were behind what can be achievable with composite reinforced by long continuous fibers. For the web-to-skin conduction welding, we used clamping tools, self-heated. So the target temperature at the tool surface was 180 degrees C, but it was difficult to control the temperature, and you can see that the temperature at the probe placed inside the tool was rather 230 degrees C. The pressure was 20 bars and the holding time 90 minutes. So in total, we manufactured 4 demonstrators. We could not see any disbonding, but we see local discoloration of the skin. At the web location, you can see that the green surface film of the skin gets yellow during the welding, and also you can see resin degradation in the web, indicating some overheating and the need to better control the temperature during the welding stage. So we did a series of tests, both non-destructive tests and destructive tests. Ultrasonic inspection has showed that there were some attenuations, so probably due to delamination and or voids, both in the webs and at the bonded joint. And that was confirmed by the micro cut we performed. You can see that on the right. We have delaminations in the webs, also voids in the 3-air adhesive film at the joint between the skin and the web. And also the 3-air adhesive film thickness was pretty homogeneous between the web and the skin, but much more variable between the 2 half webs. At the base, you can see almost no 3-air adhesive film. It has completely flown out during the welding. And at the top of the web, the thickness was close to 0.17 millimeters. So we did a study on the degradation of the 3-air film that shows that we do get degradation starting from 220 degrees C. And the temperature we used to process the material for demo was very close, as you can see, to that temperature. And we performed some TG measurements on coupons extracted from the webs that clearly showed that the TG had been reduced and that the material had been degraded. And that could explain also the poor consolidation level and poor strength of the joint between the web and the skin. That was measured by mechanical tests. So we did both pull-off test and low velocity impact test. So the pull-off test confirmed the low strength of the joint with a decrease of about 66% compared to the reference co-cured joint. Regarding the impact, surprisingly, the impact behavior was quite similar to what we have with co-cured joint, with a similar damage extent. So within AIRPOXY, we have tested a large panel of manufacturing processes involving 3-air materials to produce 2 aeronautics use cases. And here are the conclusions that we are sharing with Diego. Regarding RTM, as Diego showed, the 3-air resin has a very good processability and allows to manufacture very complex components without any additional difficulties compared to conventional resin. For SQRTM, the functionalization of the skin using a 3-air film was very successful with a very good repeatability and very good thickness control of the co-cured 3-air film. For the thermoforming, the thermoformability was demonstrated, but internal quality has to be improved, especially regarding the consolidation level. For the 3-air bonding and welding, the adhesive bonding works pretty well, and the bonding strength is quite similar to conventional adhesive film, but the welding strength was not sufficient, and on that point we need to probably increase the process window. for the repair, as shown by Diego, we get very promising results with big areas restored. But the process has to be improved to be more compatible of the industrial environment and also in-service condition, mainly by reducing the repairing temperature and pressure. So the way forward, one point of action is probably to work on the resin, and in order to increase the process window for the thermoforming, the welding, and even the repair. So currently, the 3R resin used in AIRPOXY had to be heated 40 degrees above its TG, which is 170 degrees C, meaning that we are very close to the temperature degradation of the resin. So one way would be to reduce the TG of the 3R resin, but we have not much room to play with. If we want to comply with the standard requirement of having a wet TG above the in-service temperature plus 30 degrees C. So a second option would be to add additives into the resin to promote the dynamic behavior and being able to process the 3R resin closer to its TG and staying away from the degradation temperature. We also seen that in the future we really need to improve the tooling concept in order to better control the temperature we apply during thermoforming and welding. That's it. Thank you.
Thank you very much, Diego and Thibault. I think that we have some delay, so maybe we can leave the questions for the lunch time because, well, and also during the showroom visit, people will have the opportunity to ask any questions. Thank you. Thank you very much. Okay. So to close this session, the last talk is given by Miguel Ángel Castillo from Aernova, a leading company in the design and manufacture of aerostructures such as wings, stabilizers and fuselages, both in metal and composites, for the main OEMs. Miguel Ángel is PhD aerospace engineer. Since 2000, he works for former Gamesa Aeronautica, now Aernova, where he has held several technical management and direction positions. Head of Structural Integrity Department between 2000 and 2006, Managing Director between 2006 and 2011, and since then, Vice President of Technology Development in Aernova Group, which is his current position. Before, he was working for 11 years as aerospace analyst engineer for CASA, currently Airbus, Boeing and Hispano-Suiza, currently Safran. So, Miguel Ángel, I give you the floor.
Well, thank you very much first, CIDETEC, for inviting me to be here. It's a pleasure. And thank you, Nerea, for your kind introduction today. So let me start being provocative. History is a record of effects that the vast majority of them nobody intended to produce. These are words coming from Joseph Schumpeter, that is a very well-known, was 1883-1950, a reference for innovation and economy. And with these words, I want to frame my speech today about manufacturing trends in the aeronautical sector. So basically, I'll try to come to the need of being safe, safety first. That is a characteristic of our aerospace manufacturing and sector. Then I'll try to give an overview on the context, the current context, and latest news, because you know the context is changing. What could be the trends according to my point of view? Some latest manufacturing technologies. In here, I'll try to touch into something that we as manufacturers we can recognize and to put meat, and then some conclusions. Well, safety first. Aviation is an economic sector where safety has been, is, and will be fundamental. We like to travel, but we like to do it safely. Without safety, there is no commercial travels and the economic impacts related to them. The companies in this sector, the OEMs and those in the value chain, the supply chain, such as Arnova, work to make safety comes always first. And we know how to comply with all kinds of aspects related to safety in aeronautical operations along the product life cycle. The COVID-19 crisis has been a huge safety crisis, one of a kind. In this case, a worldwide health safety crisis affecting us, the people, with a global spread virus that can cause deaths. Consequently, it's not a surprise that aviation has been severely impacted, especially during the years 2020 and 2021, where we are recovering. Safety is the aspect that most significantly shapes aviation industry. The regulations, EASA in Europe, FAA in USA work well together under the umbrella of ICAO, International Civil Aviation Organization, depending of the United Nations, that sets the standards globally for any aviation matter. Safety is in the core of any aeronautics company operations, from conceptual design and material selections to in-service support through the manufacturing processes. The need to trace all the components, maintain configuration control, inspection 100% of the parts is a key part of the aerospace business. So, what are the circumstances today that form the setting of aerospace manufacturing? And, well, this is a key question, then to formulate what are the trends. And, well, these are the most relevant to me. The regulations, I've already mentioned. We are a heavily regulated sector because of the safety. The education and training. We need people with knowledge to give value to our operations, no matter if it is in the shop floor, if it is in the, let's say, the carpet. We need people well educated and trained. Productivity is a key word for aerospace manufacturing. We need to be productive. We cannot reduce our productivity when we incorporate technologies. We need to manage the product life cycle. Even if we are just focusing on the manufacturing, the product at the end has to deliver value along the product life cycle. The business, the growth of the business, the health of the business is in the core of our sector. If there is no health on the business, eventually the sector suffers. Continuous improvement, that is another key word for our manufacturing in aerospace. Digitalization is coming transversal, is affecting all of us, is affecting the operations, and is a challenge to incorporate in our operational technologies in an effective manner. Enhance the workforce skills. If new digital technologies are coming to the business, maybe we need to reskill some of the workforce. There is a need for that. And we cannot hide. Even the people coming from the university has to come with some digital knowledge in order to be productive. Entities and collaboration. We need to collaborate, no matter if we are in a tier 1 OEM, tier 2 RTO university position. We know the value of collaborating in the European framework arena, and there is a value there. Sustainability. I think that we all agree on that. The possibilities of the new advanced air mobility. We are suffering kind of a, let's say, constraint on new developments of new commercial transport aircrafts, but these new air mobility are a good candidate platform to develop technologies for the purpose of these 5-6 passenger, 50 kilometers range, for air taxis, drones, etc. And we need platforms to integrate our technologies. And, well, our current, let's say, VUCA, which is the word for volatility, uncertainty that we are living, and the fact that we are a dual sector. We operate even if we operate in the commercial transport aircraft manufacturing sector, eventually those technologies serve for the purpose of defense. And we are not talking then about competitive edge. We are talking about defending ourselves of whoever is challenging our way of life. And all of these are coming together to create what I think is the current context. So, trends. Well, this is always difficult to. It's always difficult to make predictions. But I can give you my view from my responsibility as Vice President of Technology Development of a Tier 1 like Arnova, and I can summarize initially in three words: productivity, digital, and sustainability. Productivity for a business is key to maintain a healthy operations and financial status, and aerospace manufacturing is aligned with this requirement as it is part of the business. Productivity means to do more with less. It looks easy, but it is not. The market is demanding in an accelerated manner, and the production operations need to answer in such a way that we not only cope with the current requirements, but we anticipate future ones. Therefore, we need innovation proactively to gain productivity, so comply with the new value to our customers. The aerospace manufacturing innovation has to come to operation robust enough for not meaning a risk. Landing the concept to a more concrete manner, the technology innovation have to reach to attract the attention of the commercial people, of our customers, the famous technology readiness level 6. And in manufacturing, the manufacturing readiness level 6, meaning that the new aerostructure has been demonstrated in a soft floor environment with some prototypes in an adequate number, with enough number of demonstrators, and so compliance with the required rates. The industrial manufacturers need to achieve actual business impact from technology innovation. For the manufacturing operations, this means achieving new processes and materials beyond current state of the art that are translated to productivity gains, so we can grow and generate more qualified jobs. Impact on the bottom and go beyond the state of the art in aeronautics production. Then I mentioned digital. This is good news for us. Digital technologies can improve our competitiveness, our productivity. But these technologies, information technologies, are available to all of us. Aerospace manufacturing is no exception, and we can look for innovation that can be translated into productivity gains. This is a big global trend and innovation stream. Use of digital twins for the manufacturing process, sensors in our production floors, using eventually artificial intelligence for anticipating production bottlenecks and real-time optimization. There is an innovation trend there. What we need to know is that this trend, digital technologies are globally accessible, are accessible to us, but any other part of the world. In consequence, as we can use them to innovate, our customers, competitors, suppliers are using them as well. Furthermore, the personal costs, production costs, trend towards equality due to globalization that is here to stay. Last but not least, we need to talk about sustainability as a trend and what it means for our space manufacturing ecosystem. The need to reduce energy consumption in operations. Water contamination and other pollutants is already here and is going to stay. We need to have in mind that aerostructures are designed and manufactured for minimum product life cycle environmental impact. And this is key, as 90–95% of the impact that our aerostructures are producing is achieved through the reduction of weight, reduction of aerodynamic drag. Only 5–10% is, let's say, tied to our manufacturing and decommissioning. Of course, we need to take care, but at the end, major of our impact is in when the airplane is flying, reducing the weight, reducing the aerodynamic drag. So, as I've told you before, I'm going to illustrate some of these latest trends, manufacturing technologies, underneath an impact-oriented project to reduce aerostructures, aerodynamic drag and weight. This is Clean Sky 2, large passenger aircraft, integrated aircraft demonstrator platform for hybrid laminar flow control that will be finalized next year. Just to remember the fundamentals in wing design, aircraft design, The friction drag appears on the direct interaction of the air with the structure. Small, tiny imperfections generate flow instabilities that evolve in turbulences, generating more aerodynamic drag force. Reducing the geometrical discontinuities and the waviness, achieving accurate finishes in the leading edge area of a wing enables an extended laminarity area. This is known as natural laminar flow. But for transonic regime, as the wing swept increases, so do the cross-flow instabilities, and there is a need to suck the boundary layer in order to maintain laminarity. This is called hybrid laminar flow control, that requires a suction pump and the presence of microholes to produce the required suction. The European Commission, together with private and public entities, are active in clean aviation to support latest R&D initiatives, some of them in laminarity. And as an example, current achievement and calculations with HLFC for a big transport aircraft means up to 8% aerodynamic drag reduction. That is equivalent to reducing 5 tons of fuel in a long transatlantic flight per trip. But this project has not served only for the purpose of the final platform, but for maturing some technologies, manufacturing technologies that follow the trends that I've been mentioning before. Well, in here, so the first one I want to talk is the forming of titanium plates for natural laminar flow with complex leading edge geometry. The forming of this variable porosity with the microholes titanium sheet is the objective to obtain double curvature. Is titanium is metal. So we develop a solution technology based on let's say two streams, stretch forming and hot forming. We did all the analysis of the solution, the demonstration, and at the end, together with with our partners, here you can see some of them. I bet that some Lortec guys are in here. If not, Lortec has been a key player and a key partner of us. And the status of this technology, we are going to achieve TRL6 in Q4 2022. Another one is the quality control process and its application for micro-perforated sheet metal under industrial conditions. The objective in this case was to automatize quality control of the micro holes or large surfaces. The solution was using a robotic cell for automatic deburring and rework of the micro holes, and then do a thermographic inspection of the clogged micro holes. Here you can see the robotic cell is commissioned and is installed in our Nova Mignano facility, and there is a thermography where we can check if the micro hole is properly, let's say, open or clogged. We developed this together with Techniker, very close to here in Eibar, and the maturity is TRL6, and we have the technology ready to be in use. The laser pretreatment of the micro-perforated titanium sheet and hybrid bonding joint titanium composite. We have been talking about hybrid structure, and the maturity of them is a big challenge. It's about surface engineering to activate the bonding. The objective was to maximize the suction area, minimizing the area of bonding, so to enhance the bonding characteristics. The solution was pretreating the metallic skin, the titanium, with some technologies, laser, infrared, to achieve a better bonding, let's say, characteristics. And here you can see the results. Well, we developed this together with Fraunhofer IFAM in Bremen. You can see here in the bottom the G1 and G2 modes for adhesive and titanium are received, and then what we could achieve, especially in the G2 mode, with the infrared and laser treatment. You can see here some of the, let's say, of the surface images coming from how the infrared and the laser could activate the titanium to create good bonded joints. Yeah. TRL6, full industrial application, this technology is ready and is attracting the attention of our customer, in particular Airbus. well, last but not least, coatings increase operating life of HLFC titanium skins with anti-erosion resistant coatings. We have had in here different solutions with PVD, let's say to avoid the erosion of the leading edges together with Airbus. CIDETEC has been part of this effort in a parallel project, and we have been able to do this. So coming to conclusions, in the 5 minutes that I got left, the aeronautics manufacturing ecosystems, companies, OEMs and value chain, RTOs, institutions, we are all aware of the need to innovate. Innovation, you follow Joseph Schumpeter's theories that innovation is the engine of economy, are not new and are sufficiently internalized, which have been amply demonstrated with the economic improvements resulting from technology advances. Economic growth in any sector results of quality of employment, improved living standard and more benefits for the society as a whole. The pandemic and the invasion of Ukraine have exacerbated the VUCA context, volatility in demand, uncertainty in the future, complexity in the relationship between sectors, and the need for economic of scale as the European Union. We need it. We need economic of scales, not getting back. That's what I think. We are immersed in a process of change. Passivity is not an option. Although the urgencies to innovate are not good, and it is better to do it in good times, in situations of extreme alarm, such as the pandemic, it has served to accelerate innovation related to the vaccines, the viral research, new treatments, the digital application to track infections, and other innovations to mitigate the effects of the pandemic. Aeronautical manufacturing business needs to strengthen the value proposition. Companies in the crisis have maintained the capabilities that have taken so much time and efforts to achieve. Now we have to continue maintaining and increasing our engineering and industrial capabilities. This makes us continue developing and incorporating technology innovation that results in increased competitiveness and digital transformation that increases productivity. Companies that innovate generate business opportunities that present challenges for R&D. In this way, aeronautical R&D can generate new knowledge and technologies that are sources of future innovations, closing a first virtuous circle of economic growth and future social benefits. The need to maintain and enhance our education system in excellence. This is research to generate new knowledge. Teach the physical and mathematical fundamentals that are the basis of a good aeronautical and manufacturing engineering. Maintain the state-of-the-art academic training level with high-level scientific technology professors. This is a long-term investment, but one that returns benefits greater than the cost and efforts involved. Training is essential to have quality R&D. In turn, quality R&D improves education, pulls it in, and as a second virtuous circle, generates results that in improvements for economic agents, growth and more employment and improvement of the society. In aerospace, we always have to think about safety in our operations. I've already mentioned the safety related to the virus, but safety is also related to cybersecurity nowadays, as we are digitalizing our processes. So we need to take care of this aspect that is key on our business. All aspects of sustainability and minimizing the environmental impact. We have been hearing this morning a lot about this, related to the reduction of the fuel consumption, improvements in reducing weight, aerodynamic drag. In this sense, the substitution of fossil fuels for sustainable aviation fuels, neutral in CO2 emissions, is going to be a line of innovation. Also, the development of electric aircraft platforms, hybrid propulsion plants in the range of 50 passengers could be achievable in 2030. As a matter of fact, Arnova is collaborating with HAR-19 in developing a 90-passenger full electric commuter aircraft. And more in the long term, hydrogen as a source of energy and the challenge to integrate liquid hydrogen in an airplane or as a part of a fuel cell or direct conversion. Technology innovation will be then intersectorial, as space is well ahead of us in using hydrogen, cryogenic hydrogen, and automobile industry is well ahead of aerospace in hybrid electric engines. So in this case, innovation will be adaptation. Industrial companies like Arnova need to maintain a healthy business. Well, this looks obvious, but it means more than ever that we need to uptake research and development and innovation results to make an impact into the market and grow. That means to attract the attention of our customers. This means enhancing our value proposition, reducing extra costs, optimizing operation, reaching higher level of efficiency, designing manufacturing processes, etc. Digitalization, I mentioned, is a key enabler for design, manufacturing, validation, certification, MRO. Air transport is a system of systems, and we need to use all digital tools and to innovate with them, integrate them in our components, vehicles, products, services, etc. We need to be effective in our investments. And as such, in Arnova, we are concentrating our investment in R&D and I in three key aspects, three key streams. All aspects related to improving our competitiveness in our context with the development of new, more productive and efficient operations based on digitalization, new materials, concepts and production processes for aircraft that provide new value to our customers, and developments aiming to reduce the environmental impact in the product life cycle. In any case, we must redouble our commitment to innovate. Having the will to innovate can arise spontaneously at an individual level and then be promoted by companies and institutions. In technology-based industrial sectors with complex systems like ours, we are required to encourage the aspect of willing to innovate, the motivation, as this is a heavily regulated sector due to the safety. Innovation, in particular technology innovation, sometimes has been perceived as attacks of the educational system and the RTOs. Companies also have to stimulate the incorporation of innovators, stimulate collaboration with academia, with technology centers, SMEs, startups. The culture of entrepreneurship in students can be promoted more, facilitating spin-offs in universities and technology centers. Why not culture of intra-entrepreneurship in companies? And lose the fear to fail. Inculcate the principle that sometimes in R&D it's good to fail. I mean, you don't meet the requirements, but you have a lot of lessons learned that you will be applying for future success. This sometimes creates more value than being very successful in R&D. And being agile. R&D must be based on projects that involve multidisciplinary teams, digital, etc. Transversal, open innovation between university, technology centers and company. Essential to have companies and entities convinced on the need to invest in R&D and I, and the institutions coming with us in the lowest TRLs, as in these times is difficult. And this is all that I wanted to tell you. I hope that you have enjoyed, and thank you very much for your attention, and maybe the questions during the last time.
Thank you very much, Miguel Ángel. I think that it has been a very nice presentation. We are late, so we have to go for the other room to start the lunch. So I think that, well, maybe we can delay some minutes the next session, so we can start the last session at 14. Huh? We will delay 10 minutes, okay? So that we can have enough time for the lunch. So enjoy the lunch and see you later.
Okay, so good afternoon, everyone, and thank you for attending this last session. In this last session, we are going to focus on sustainability aspects of composite materials And in this last session, we have 3 speakers: Caroline Petiot from Airbus, Alkis Paipetis from University of Ioannina, and Alain Graillot from Specific Polymers. So first, I would like to welcome Caroline Petiot, our first speaker. Caroline works for Airbus Central R&D organization since 2017, where she occupies a position of senior composite scientist. She joined aerospace industry in 1990 and contributed to several researches and innovations in polymer fiber reinforced composites, contributing to their successful large introduction into aerospace products. Her actual field of interest is on developing high-performance, greener polymer composite materials with end-to-end functionalities for circularity and environmental sustainability. And today, Caroline will be talking about sustainability aspects at Airbus. Thank you, Caroline. You can start.
Thank you very much for this introduction, and thank you very much also to CIDETEC for having invited me to be with you today. It was a very good opportunity. So for more than 50 years, Airbus has remained at the forefront of advancements in aerospace. However, our world is changing, and so we are changing. We need to move forward. At Airbus, we want to be known not only for our exceptional products and services, but we want also to be recognized for the positive impact we have on the world and its citizens. So sustainability is not just managing environmental concern within Airbus. It's also to develop and improve a human experience within our business. So I will talk about the challenges and opportunity towards sustainable composite, as said. And I will start with presenting our ambition. Then we'll see how we plan to decarbonize and reduce our environmental footprint, introduce also circular economy principle, and then get to a very short conclusion. First of all, in terms of our ambition, we've got several aspects in that, but for today's talks, I will only focus on the leading the journey towards clean aerospace. About leading the journey towards clean aerospace, I will introduce the lead to the decarbonization of the aerospace sector, bringing first zero-emission commercial aircraft to the market by 2035. So this is the first element. We'll work on reducing our industrial environment footprint, including our supply chain. This is very important. And we will also put into place the development of a more circular model with leveraging eco-design and digitalization, as already presented in some previous presentation by previous speakers. Then, regarding the decarbonization roadmap for European aviation, Airbus is committed to meeting the Paris Agreement's targets. For 1990, the industry has managed reducing its emission per passenger and per kilometer by 50%. So we are for a long time working on reducing this emission. Nevertheless, in October 2021, the industry as a whole committed reaching a zero-emission target by 2050. So this is what you see as an illustration on the slides. In order to do that, we need to call for multiple solutions. First of all, using sustainable aviation fuels and alternatives. And this will account for minus 34% of the efforts. Then we need to work on improving the air traffic management and aircraft operation overall, work on economic measures, And last but not least, improvements in aircraft and engine technology. And this will account by overall 37% of the total efforts. And this is why we are together today to exchange further about these aspects. So you've all heard in the press that we are going to develop a zero-emission aircraft to be ready by 2035. And for this product to be operated, we are considering using hydrogen. So why now hydrogen? It's because it emits no CO2 and has the potential to reduce the non-CO2 emissions as well. Then we account for the cost of producing H2. And this cost is likely to decline as many industries will adopt the solution of hydrogen. So we count on that. Then on the top, as already introduced by some other speakers, the versatility of the solution is quite attractive because it could contribute to sustainable aviation fuel, but also be used directly on board an aircraft through direct combustion or fuel cells. Now, regarding the issue and the challenges in using such a kind of solution, we will compare there the usage of kerosene regarding weight and volume versus hydrogen, and this for the same amount of energy. This is what is presented on the left-hand side of the slide. So first of all, H2 is 3 times lighter than kerosene. And moreover, when we look to the volume, it opens a new challenge for us because 1 liter of kerosene would be equal to more than 3 liters of hydrogen stored under 1 bar, so huge volume there, or 6 liters of pressurized H2 under 700 bar, or 4 liters of liquid hydrogen. And this is where we are, because we need to keep the volume as small as possible and the containment as safe as possible. So it was chosen to down select a liquid hydrogen storage solution, which means a constraint in terms of storage temperature to have this liquid phase, which is to be kept at minus 253 degrees C. And it opens a really tough challenge, especially for composite materials, but also metallic materials, to have those extreme temperature and sustain. The material should sustain over the full lifetime of the aircraft, those temperature. It means also we've got a challenge and needs for new development of super insulation material to make sure that the inner vessel envelope could be maintained at this temperature. And this could be achieved with vacuum, but we could also think of new lightweight material to find new solution. And composite materials are lightweight candidates also for H2 tanks, even if in the press you can read that we are considering metallic solution as well, as introduced by José previously. We are competing with metallic technologies. So it offers, in terms of TG, regarding resin system, also new opportunity, because the operating temperature, we are in the very low range there. So we should think out of the box and try to do our best and develop the best solution. Then, environment responsibility within Airbus has to be considered over the entire business, as you see on the slides. Starting from design, investing in R&D, design, thinking also in terms of design windows, as we think about process windows all the time. Design windows should be reopened when we face a too restricted process window. Maybe we have a solution in the design window, in reopening the design to see whether we could get more flexibility in finding a solution. The supply chain, we need to work closely with our suppliers because We need our suppliers to comply with our environmental commitment. And in terms of manufacturing, we've got ambitious goals to reduce our manufacturing footprint and promote conservation of resources and better manage this industrial footprint. It was said previously, ideally, we would like to have no waste. So we need to have an excellent buy-to-fly ratio and maximize it. Operation, we need to optimize the aircraft operation and maintenance to achieve optimal noise and emission as well. And for sure, in this exercise, repair management is important, and repair solution is important, and end-of-life recycling, such as to be able to dismantle an aircraft and segregate the material, such as to maximize the reuse and upcycling eventually of this material, prefer to downcycling. If we can upcycling, we will make the best out of it. Now, regarding the circular economy at EU level, there was some directive towards the zero waste program for Europe, which established the waste hierarchy from prevention, first of all. How we will prevent producing waste, then afterwards reuse, consider reuse, recycling, energy recovery, and disposal. And this has led to 6 waste directives, starting from raw material, going through the design, production and remanufacturing, also distribution, consumption, reuse and repair, collection and recycling, lastly. In terms of circular economy priorities, for design and production, we see low waste and no waste, as already said, but also sustainable materials should be rich compliance, substance-free rich compliance substance. For example, for composite material, epoxy resin system, for example, we'd like to get rid of bisphenol A in the future, because this is known as a endocrinian perturbator. So we need to think from now how we will achieve such a target for future material development. As an example, and there's many other substances with environmental concern we'd like to get rid of. Design for recycling, so this has been already discussed and introduced, and also low energy consumption, production environment. In terms of operation of use, we look for efficiency, so high performance materials, and we've got a joy there within composite, which is the use of carbon fiber. This is today why composites are so efficient, because the resistivity versus the weight is excellent. Durability was said, our product should last for long and be reparable as well, and be low weight to be efficient in usage. For end of life, recyclability, but also when we face material mix and we have material mix, we need to be able to segregate them easily when we dismantle, to be able to reuse and find new disposal routes. Just to give you some ideas, some example, what means sustainable raw materials. Sustainable raw materials could also use bioorganisms, make use of catalytic chemistry, such as to facilitate the end of life or reversible principle, as we've seen with the Vitrimer developments. For thermoset composite, we look for biodegradable polymers, decomposable resin, reshippable composite, as shown today, discussed, reformulated polymers with also recycled content, because composite sourcing is bio-based, but could be also sourced from waste of other industry to build new solutions, also for aeronautics. Recycle and reuse endless fibers in high volume fraction, because as seen and as seen today again, we have product and we have composite with 60% of carbon fiber in it. So to do that, we can develop new UD mat, and a good realignment should allow putting more fibers in the mat. Reprocess fibers in continuous format. It is a question mark. What can we do? Because we still lose the continuity of the fiber at end of life. In terms of bio-based polymers, Furan resin system looks most promising thermoset bio-resin system for interiors application, for example. So we are moving forward. We are finding solutions such as to move forward. For thermoplastic, increased use due to inherent reprocessing capability is a very, very important aspect. Recycled and reused endless fibers polymer as molded compound, new shape format. I've listed there also biosourced polyamides because we found it in the market actually, derived from castor oil. And in terms of sandwich structure, we need to work towards developing new core materials. As today's standard is aramid paper with phenolic matrix. Alternative could be recycled carbon fibers, base core, wood core, or thermoplastic foams, for example. In terms of polymers transformation, this is quite important. I've listed there the potential uses of biotechnology or life science and reactive chemistry, like for enzymatic purification and sorting. I've listed lignin because lignin is one of the most abundant polymer on Earth. End-of-life decomposition and metal sorting, like metal leaching from bacteria. This is for lightning strike protection and separation, segregation of the material and electric system. Activation upon demand, and I will list there also carbon fiber. Carbonization to get those carbon fibers is really energy consuming. Therefore, the cost will increase. We need to do something to find some alternative heating system. Auxiliaries, that was already presented by José, and composite semi-product with reactive resin system, low energy demanding system. We can imagine to have system which would start on demand, fast curing, out of oven principle, efficient tooling curing, heating system. We want to heat the part, not the tool. The heat should be in the part. We want low inertia system, and continuous production line with online monitoring system for quality control. Reducing the environmental footprint within Airbus means reducing water consumption, energy, CO2, and the volatiles, and also waste and raw materials. By ratio moving from 50% up to zero for the volatile, but from minus 63% for the CO2, for example, and the waste reduction should be minus 20%. Environmental footprint within our operation compared to manufacturing, you would see that the consumption, energy consumption, comparing S320 there and S350 is linked to the operation of the aircraft. And the manufacturing, the production of it is very, very low. This is the message. And that's over the overall lifetime of the operating the aircraft, just to give you a picture. And then circular economy is really inspiring. There's cooperation ongoing, and it's just to give you a flavor of some of them, because they are much more numerous. Like, for example, developing a monohull sailing yacht, cooperation with for the IMOCA yacht, using some declassified carbon fibers from our plants. Other example with Petit Breton Company for bikes, production with unused carbon offcut from production. And third example just listed there given is the reusage of recycled carbon fiber for cabin panels interiors. So all this is described in the press, and you could have a more detailed look. So in terms of conclusion, composites are really opportunities as lightweight materials. we still need to work on that and still make them lightweight, considering also carbon fibers on new formats. We could do better. Minimize the use of materials, reduce the waste, repair them, and we are on the good track. Disassembly and segregate, and ease the end of life and the reuse and repurpose of these composite materials. Recycling, at last, is the last option. Bio-based with recycled content, we should look for also. Substance compliant, and also the mindful use of critical raw materials. For printed electrics kind of materials, we need to retrieve the metal and separate it from the composite. It is of value. Thank you very much for your attention.
Okay, thank you, Caroline, for this nice presentation. And now, if you have any questions? No? I have one question. I would like to know your opinion about these bitrimer materials. What do you think? Do you think that could be a suitable candidate to replace the actual thermoset composites or not?
I think we are on a good track, but we still need to further demonstrate the viability. For example, you've listed in your presentation, earlier, that we should demonstrate how thermostable they are over the long lifetime. So I would like to see creep evaluation as well to show that it is viable, that we won't face some issues after some years of usage, as an example. Then the process windows as it is today is a bit restricted as discussed, but why not reopening the design window in front of this process window? Could we reconsider a bit the way we do the stiffening today, just to relax the constraint? And then maybe the TG, whether we could find some eligible parts with maybe could tolerate a lower TG resin system in some areas, such as to get more freedom in processing the solution. So yes, you are on a good track, but still some work.
We will take into account.
Thank you.
Thank you. So now let's continue with the session. Our next speaker is Alkis Paipetis. Alkis is a professor at the Department of Material Science and Engineering of University of Ioannina. Currently, he is vice-chairman and the director of the postgraduate course Advanced Materials, organized by their department. He is a mechanical engineer with research activity in the field of mechanical behavior and non-destructive evaluation of composite materials and structures. His research in the area of advanced composite materials is focusing on techniques of structural health monitoring, smart and multifunctional materials and structures, damage mechanics, experimental micromechanics, as well as advanced monitoring and testing techniques. Alkis funded the mechanics of smart and composite materials laboratory in the University of Ioannina. And today, Alkis will be talking about structural health monitoring technology developed in AIRPOXY project. So, thank you, Alkis. Now the floor is yours.
Thank you very much, Alaitz. First of all, let me thank you and CIDETEC and Nerea for giving me the opportunity to visit again this amazing place. I don't know how my presentation will appear. Just the next one. Oh, perfect. So I'm Alkis Paipetis. I come from the University of Ioannina. This is the last talk that is related to the AIRPOXY project, I believe, in today's program. And as the University of Ioannina, we explored better the opportunities to apply SHM methodologies and include them in the AIRPOXY technology and develop them together with the AIRPOXY technology. This is, let me just see what page down is. Yes. This is our lab. We are located in the University of Ioannina, northwest of Greece, for those of you that know. We have a purposely made lab to study advanced materials, advanced composite materials, advanced polymer composites. And this is why we have developed purposely made equipment to be able to do that in various systems, mostly related to aerospace technologies. So, as it has been said a lot of times today, starting from José Sánchez this morning, we are focusing on multifunctionality. What we have identified is that this is definitely a very, let's say, an opportunity in composite materials, because what we can do with multifunctionality, or what composites allows us to do, is to architecture the material and include functionalities that will add added value to our structure, to our component, starting from our material. So our work has a lot of aspects. We have been working on hybrid and hierarchical systems. We like to do this, we like to stress this difference between these two categories. Hybrids are systems that comprise more than one reinforcing phases, probably at different scales, at different and different materials. Hierarchical materials are more architectural materials, whereby the reinforcements are linked together, so as we are able to reinforce in a more organized way our structure and give the functionalities that we want to give in a more controlled way. We have worked in self-healing materials as well, developing all relative technologies like capsule-based or vascular-based or intrinsic self-healing materials, which was actually what the technology that we tried to transfer in the AIRPOXY project, because we had worked with reversible polymers, BMIs, in the past. And all these technologies are linked together, because we say reparable, and in other sectors we say self-healing materials. It's not exactly the same, but it's very well related. And to this end, we have developed equipment that allows us to make our own prepregs, and we have different stations within this prepregging machine that we can apply different coatings, we can apply different sizings, we can make resins. I think we have used this machine to make 3R prepreg as well. And of course, within all that, because we are studying functionalities, we have developed and acquired conventional NDT methodologies and developed our own NDT methodologies that include acoustic, include electrical, include thermal, etc., so as to close the envelope of our study, which is, this is our approach. I mean, we are focusing on polymer composites and their hybrids. We are looking at all scales, and this is where architectured material is fitting, actually, from nanoscale to macro scale, and we are linking all three things, performance processing and advanced materials in terms of strength to weight or stiffness to weight ratio, by using all these peripheral techniques so as to achieve the smart multifunctional composites that we want to achieve. Within this, we have gained significant experience in several structural health monitoring techniques, which include acoustic monitoring. It says acoustic emission, it's ultrasonics. There is something that never reached the server to be corrected. So we have correlated specific acoustic signatures with guided waves from the composite, so as to be able to define the different stages in the fatigue life of the composite. We have been working with a new class of fiber optic sensors that allow us to have distributed sensors throughout the sensing length, without having to include Bragg sensors in very specific sites. And we have developed in-house technologies that relate to electrical and DC and AC methodologies that may allow us to monitor damage throughout the life of the composite, and of course topographic algorithms that allow us to see the damage, for example, the impact damage in this case, of the composite by making, let's say, a potential mapping of our composite system. This is an example. This is a technology that we have been using in epoxy as well. This is impedance spectroscopy. That is a spectrum of the electrical behavior along, let's say, from DC to something like 1 megahertz AC. And what we have been doing here is that we have been making a grid, painting practically a grid within the composite that can do we have a pointer or something? No, okay. Ah, does it work here? No. Okay. Never mind. Okay. So what we have been doing here is that we have painted a grid of, let's say, conductive layers within the composite. This actually improves the interlaminar properties, and this creates a grid of capacitors within the composite, and we can monitor damage within the thickness of the composite and actually map the damage through thickness and along the XYZ in the composite via taking impedance maps of the composite. At the same time, another technology that is being used in epoxy is well known, is the piezoresistivity of composite structures, where we can have both information on damage accumulation and elastic deformation. You can see here that, can you see it? No. Yeah, okay, I cannot see it. You can see here with the red line that you have a real-time monitoring of the stress state of the composite. And if you go to zero stress, you can see that we have an increase in residual resistance, which is characteristic of the damage of the material. If you do this for fatigue, for example, we have done it, we have published it, you can see the full fatigue curve of the material in resistance scale. We can use these methodologies to monitor on light damage and healing, something that we try to do in epoxy as well. And what we show here is that we have a modified healing agent, a capsule that has conductive elements, I think it's graphene or nanotube or something of the sort in this situation, together with a conductive healing agent within the capsule. And this capsule can heal at the same time the mechanical and the electrical property of the composite. And we can monitor this healing process. This is the damage process, and this is the healing that follows the initial damage of the composite. This is the full curve, and this is just an expansion of this curve. And of course, we can see here, as is defined by the full impedance spectrum, a body plot, that we have full healing of the electrical properties as well. Repair in aerospace, this is what I'm going to show now, is a typical project. We worked on a smart repair project, it was some time ago, where we tried to let's say, apply all these concepts in realizing what we call the smart repair system. And we applied multi-platform, non-destructive, let's say, strategy on an aircraft, on an aging aircraft wing. That's a Pedgetel rear tail wing, and a composite structural detail So we could at the same time use impedance, electrical topography, surface waves, and use ultrasonics and thermography as our benchmarking methodologies. This was the idea, so that we could monitor in real time through an, let's say, multiplexing strategy and the electrical properties, the possible evaluation of a critical crack on the patch, on the repaired aircraft structure. And this is what, as a showcase, what we worked on in AIRPOXY, where, as Stefan very aptly showed to you in the morning presentation, what we are actually doing is that we perform a heat and a pressure protocol and try to repair the damage in various damage scenarios. And we are using these technologies to assess the repair process. The concept is that this process can be repeated all the times, and we can do consecutive, let's say, loading and evaluation cycles to see the reparability of the composite. The ND methodologies that we have been applying within the concept of AIRPOXY is acoustic emission as a benchmarking methodology, IR thermography that gives us the opportunity to monitor, to visualize in 2 dimensions the state of damage in the composite, both in phase, pulse phase, and lock-in configurations. We applied the electrical resistance change method, the impedance spectroscopy, that is the full spectrum of the AC response of the material, phased array ultrasonics as a benchmarking methodology, of course, and in the end, a CT scan that was subcontracted to Diondo GmbH in Germany, because we did a full CT scan of the demonstrator. It couldn't fit in our machine. So this is what I'm going to present here. Some of the results that are analyzed, and some of them are being actually under review now to be published. Now we have specific geometries that we have tested, typical geometries like the mode 1, so that we can evaluate the efficiency of the 3R technology in various configurations, specimen configuration, and in this case, we are using the electrical resistance change methodology, and we can see the different areas that correspond to the loading of the mode 1 specimen, and how this behavior, the electrical behavior, changes as we move from the undamaged specimen, the pristine specimen, to the repaired specimen, with the relative explanations that correlate directly to the repair mechanism as it performs, and, as we have seen, the flow of the 3R resin within our, let's say, coupon in this case. Within AIRPOXY, we have developed a different geometry. This is the lap strap geometry. It's a very simple test, actually, whereby we have this lap, the bottom part, and the 2 straps on top. This is a typical end up, so the specimen is clamped here, and half of the right tab is clamped there. And as we tension the specimen, at some stage, we have a mode 2 crack initiating there. It is a mode 2 crack that progresses to change to a mixed mode crack, as we have seen from simulation studies. And we can verify this change by a drop in the load curve or a discontinuity in the resistance curve. So there are different reasons why we have all these changes in the electrical resistance curves. We always do get a very clear discontinuity. You can see that our structural health monitoring, let's say, strategy can follow all the damage that can reflect all the damage or all the behavior that we can see in the load displacement curve of the repaired specimen, and we can see in the acoustic emission profile as well, and the acoustic activity profile, that in the first case we have an outburst of activity prior to the failure or at the moment of failure, whereas in the repaired case we have a full spectrum of activity, which correlates to something what we would call, the felicity effect. There is damage there, or there is complete repair, or there are several reasons which we have described within the epoxy project. Another very typical evaluation is that we can see that the resistance is a direct measure. The resistance after the repair is the direct measure of the efficiency of the repair, and we have seen that this measure, this metric, does correspond to the repair efficiency that we get. 5 minutes more? Okay. Okay, sorry about that. Here you can see the C-scan of the damage and the respective images we get from thermography, which evaluate, and you can see the very good repairability of the 3R resin, but this would not, will not prevent the larger extent of damage in the second impact. And in the last slide of this presentation, I will show you the computer tomographic images of the full transverse stiffener that was shown to you by Diego earlier this morning, where we can see the damage after the purposely built, let's say, loading that CIDETEC made to the transverse stiffener, and how this damage is actually healed after the repair process that was performed in CIDETEC with the tool. I think you can see it there. It's on the table, and even we can see some little faults that relate more to the repair process than to the actual properties of the 3R. So this was a full success, I would say, in terms of the demo. Of course, this was all due to AIRPOXY and the team of CIDETEC that practically had this initiative. Thank you very much for this. And if you have any questions, I would be glad to answer them.
So thank you, Alkis. Are there any questions? Okay.
Thank you very much, Professor, for your presentation, and congratulations again for the project, which is very interesting. My question is related with the scale-up of the self-sensing materials.
Yes.
Not only in the manufacturing, which is also a challenge, but how we can monitor large structures with self-sensing materials in terms of how to detect the position of the damage. I think it's a challenge, and I would like to know your opinion. Thank you very much.
There are very specific problems that relate to that, and the first problem relates to typical problems like contact resistances and how this change, but we can overcome that going to the dynamic measurements, the AC measurements, and what we have seen as the best solution, because it's the least structurally aggravating and can be even beneficial to the structure, is what I showed you here. That is, we actually paint the conductive elements within the structure, and this can give us damage topography very accurately. Then the problem we have is multiplexing. This can be included in the structural design. I mean, you can do the multiplexing by painting the relative network within the composite. That's what I think. In terms of bulk measurements, this is the work. You can see it here, practically. This is a typical damage topography image of the lamination within the plate after impact damage. What is the problem here is that you get, let's say, topographical information with a certainty less than 70%. If you have, for example, a high velocity impact damage there. Because it's very difficult to solve the inverse problem. You have a lot of noise there. What we have tried to do biased measurements, I mean putting current or voltage and see the respective voltage board or current change. This improves the signal to noise, but not that much. So I think that the best way to go forward is to make what I said earlier, an architectured material that can do a lot of functions. For example, we are working on making metamaterials that are high-frequency filters by painting the grids in specific spacings within the composite, which is a very good idea. I mean, you are free to steal it. I don't know, I think this is the way forward. I think this is, you don't have the problems that you have by modifying fully let's say, the matrix, which gives problems with viscosity, for example. That's my sense in it. You're welcome.
Okay, so thank you. I think that we don't have more time for questions. And now, finally, to end with this sustainability session, we have here Alain Graillot from Specific Polymers. Alain is graduated in chemical engineering, and he obtained his PhD degree in polymer chemistry in 2013. He joined the Specific Polymers team in 2013 as a research engineer. And today, Alain is the Chief Operating Officer of the company and lead industrial and collaborative R&D projects. He has more than 12 years experience in the field of polymers and material chemistry. And within Specific Polymers, he now leads multiple collaborative projects where he uses his expertise in various research areas, biomedical and nanomedicine, sustainable thermoset materials, polymeric materials for energy, and high-performance materials and coatings. And thank you, Alain. I think that you can start with your presentation.
Thank you, Alaitz, for the introduction. And thanks a lot to CIDETEC and Elena especially for giving me the opportunity to present specific polymer work in this area. So today's talk is about chemical design of sustainable resin for build-to-spec thermoset materials. But before going a bit deeper in this subject, I would like first to give you some more input about the company and what we are, because I think it's important to understand where we are in the supply chain. So first about our activities and skills. So Specific Polymers is a SME company. We are 27 people, mainly acting as a research and development service providers for industrial partners and in the scope of collaborative projects. And so we design new materials with the idea to validate proof of concept. So we are really at the bottom of the value chain, trying to define new materials for the future. So we are working worldwide. We are selling products all over the world. It represents approximately half of our turnover. We are selling products, but mainly the main part of our turnover is based on the selling of research and development projects. So this is our skills. So at the early beginnings, the activity of the company was geared towards the synthesis, the ability to synthesize custom design polymers with very specific functionalities. And so I would say that about 80% of the molecules that we are proposing in our R&D portfolio is products that are not sold anywhere else. So it's not really interesting it's only interest very specific area, a few people in the world, but we are the only companies that are selling these products. So polymer synthesis at the beginning, and time by time, because we needed to go closer to the market, we developed a formulation of resin activities, and the idea was to, based on our understanding on the chemistry of the resin, fully design a resin formulation that is consistent with the specification linked to the implementation processes and linked to the final applications. So it's really designing the formulation to reach objective and not bring a formulation with its own specifications. Design off is just to mention that we can take a project since the early beginning, defining strategy to push forward at the experimental part, and physical chemical characterization because we are characterizing all the products and all the things that we are doing. And industrial transfer, it's an activity that is getting more and more important in the company, because each time when we are developing a new molecules, a new polymer that is interesting, the next question from our customer is, okay, it's interesting, it's good property, but what next? And what next? We need to produce it, and we need to find a way to produce it. So we are working more and more with tool manufacturers in order to transfer to them our synthesis process, optimize them, in order to produce at first 1 kilogram and then 25 kilogram, and then give enough matters to validate the proof of concept in some applications. So this is what we do. In which areas? So we have 4 main areas: high performance materials. So it's mainly dedicated to aerospace and aeronautic applications, because as it was mentioned today, we need to get composite material which has lightweight but can compete with metals in some applications, so in some hot wet zones. So you need to have some resin with very high thermomechanical resistance. So it's what we are trying to do. Also, we are working in some specific coatings with some specific hydrophobicity, or oleophobicity, or conductivity, because we need to solve out some issue also in this area. We have more and more work at the moment in the field of energy, mainly lithium batteries, developing solid polymer electrolytes in this area. Environment, I think I will go deeper in the next slide, so I will not talk now about that. And the last part is health. It's more, I would say, for the moment, it's not something we pushed for the moment. It's more an opportunity, because we are able to design some specific polymers. But it's something we would like to develop in the future. So now going deeper on the main subject of this talk, so chemical design of sustainable resin for build-to-spec thermoset materials. And to start explaining what we are doing in this area, I wanted to show some slides about the current situation and where we are now, which explain what we are trying to do. So it's somehow gives some echo to what Philippe Christou explained this morning. So at the moment, in the field of epoxy, as you may know, 80% of the resin are based on bisphenol A diglycid ether, so epoxy resin. It's aromatic, it gives good properties, good chemical resistance, it's low cost. So I would say, apart from the sustainability aspect, it's perfect. The second resin that is interesting in Novolac-based epoxy resins, so it's the one that is the oligomeric one that is here. So it's also interesting in terms of properties. Then in a lesser extent, you have cycloaliphatic epoxy resins that are used in some application, for instance, for avoid any yellowish of epoxy resins. And then you have other kind of aliphatic epoxy resins that are used and formulated with the others to adapt the properties and give interesting formulations. So this is where we start, but it has some issue. It has good property, but it has some issue. It's synthesized from various compounds that are toxic and damage the environment. So epichlorohydrin, it's highly toxic and classified as substance of very high concern. If we speak about epoxy Novolac, it's based on phenol and formaldehyde, which are also very toxic compounds. And finally, if you want to make bisphenol A diglycidyl ethers, it's based on bisphenol A, which is very harmful. And as it was explained by Caroline earlier, it's something that we need to try to figure out to propose something else. So this is the point, the toxicity. Then most of it is petro-based at the moment. So we need to find alternative feedstocks. And finally, as we all know, and I think it's the main subject of the day, thermoset resin are not recyclable at the moment, and we think we need to find alternative to consider the end of life of such materials. So the foreseen solution at the moment, and it was also explained this morning, it's epichlorohydrin, and its brand name Epicerol can be bio-based. So now it can be made from natural glycerin and hydrochloric acids. So it's a way to obtain partially bio-based resins. So this was explained this morning. And a second aspect, you have different kind of aliphatic epoxy resins that are based on paper or sugar industry, biofuel industry, or for food industry, that can give epoxies and can be used as in resin formulation in order to increase the bio-based content. But the problem is these resins are low performance because aliphatic, and so you cannot push them too fast, too far, because if you want to reach higher performances, they are not consistent. So this gives somehow the point where we start, what we want to do. So the problem is JBA is still the main component, and we need to find an alternative. Okay, it can be bio-based, but for the moment it's mainly based on epicerol, and even if it's bio-based, it's still toxic. And with this solution, as it was also explained, we can only reach bio-based content from 29 to 66%, which is not that high at the moment. And I mean, it's good to have that already, but we need to go further. So within specific polymer, we are focusing on I would say the core of the epoxy, so the phenolic or the alcoholic compounds that we use to make epoxies, and we are focusing at the moment on derivative from sugar or from lignin, and I will explain a bit later. So our whole strategy is based on this, I would say, value chain, or all steps to make a material. So first, we really consider the raw materials, trying to figure out what is the most interesting biomass that we can convert into epoxies. And I will explain what is the main criteria that we are taking into consideration to select these raw materials. Then in our chemical processes, in order to make the epoxy out of these precursors, we are trying to use green chemistry principle to have eco-responsible approaches. And then we are also thinking at the early beginning of the conception of the material of impart into this material reversible bonds in order to achieve 3 art properties that it was explained today. So this is our strategies. So if I go back on the selection of the precursors, so the main aspect we are taking into consideration when we select some precursor from natural resources is first the naturality, of course, their chemical structure. What we want to do is to have I would say a range of properties from low TG to I hope high TG in the future. And so we are selecting aromatic, aliphatic, cycloaliphatic compounds in order to have this variability. And also in terms of physical property, you need some molecules that are viscous, you need some molecules that are very liquid, and play with them in order to make a suitable formulation. So this thing we can tune at the early selection of the chemical structure. We also have a look on the access of these resources and abundancy, because it doesn't make sense to develop a full resin on a precursor that cannot be produced in sufficient volume for the application that is considered. And of course, we also look at the toxicity. And then when we have identified the precursors, the objective is to convert them into epoxies, and time by time go to a production at least 30 kilograms in order to achieve some test. So this is some chemistry. I'm sorry, but I need to show chemistry of the main precursor we developed in the past, and we made a differentiation in between sustainable epoxide and bio-based epoxide. So what we call sustainable is we know, or we are pretty sure that it's interesting alternatives that can be bio-based in the future, or that the supply chain to have it bio-based in the future is already starting to be developed. But for the moment, what we sell, it's petro-based. But at least it's not JEBA and it's not toxic. So for the moment, it's what we sell, sustainable epoxy. So it's based on vanillin alcohol, it's based on fluoroglycinol, resveratrol. So this is all aromatic phenols that can be extracted from, for instance, from wine residue or for algae. And we convert them into epoxy, and we work on the chemical synthesis in order to have something relevant for pilot scale. And then we have some bio-based epoxies from isosorbide, for instance, which is this cyclo-heteroaliphatic compound that is on the right-hand side. We also work on a derivative from cardanol, which can be extracted from cashew nuts. So it's, I don't know, is the mouse, whatever. It's on the right-hand side, the one with the aliphatic chain and the aromatic ring. We are increasing the epoxy content to increase the mechanical properties, and we have done a huge work on epoxy vegetable oils in the scope of one previous project called ECOXY, in which we were able to design epoxy vegetable oil with very different content of epoxy, resulting from the different content in saturation. So we have these precursors, these epoxy building blocks, and then we work on their formulation to address some business case. So each time the idea is to tune the resin composition and to assemble all the precursor in order to reach first the process specification. So for instance, adapt the curing cycles, adapt the performances, have the proper reactivity and stability depending on the processes. And then we address, depending on the project, this resin to different kind of application, mainly in aeronautic, automotive, construction, and energy. How we design our formulation? So as I explained already, we need to define the specifications that are linked to the implementation process, and the main performances that need to be reached when the material is cured. So it's aspects like viscosity of the resin, the curing cycle, the reactivity, gel time, post life, what is the thermomechanical performances, and maybe in some cases you have some other properties that you want to put. So in terms of methodology, we always act the same. We want to define a petro-based resin that is a reference resin, which gives us the values that we need to target. We characterize this resin, and then we try with the bio-based or the sustainable alternative to make something that brings the same properties in terms of rheology or thermomechanical properties. We make the building blocks, we make the resin formulation, we make a pre-screening at lab scales, we evaluate the results, and then when we have the base candidate, we work for the pilot scale transfer and optimize the process to produce more quantities. So this is basically the idea for the bio-based part. So now if I go to the end of life of the thermoset, and Alaitz already presented everything this morning, but basically the idea is to work around dynamic and reversible networks. So there is different kind of approaches. It can be supramolecular dynamic networks, which is mainly a physical interaction. In our case, we are more on chemical interaction and associative CANs, as it was explained already by Alaitz earlier. So if I focus on what chemistry exactly we are working on, so mainly three kind of chemistries: transesterification, transamination, and disulfide metathesis. So this is the three reversible chemistry what we are trying to put into building blocks in order to insert the building blocks into the materials, and then by the end of life use this reversibility to access to chemical recycling, reparability, and reprocessability, as it was done in the scope of AIRPOXY. To finish the talk, I just would like to say some word about three projects that we, past projects or projects that are ongoing, which really show all that I explained on our approach and methodology. So ECOXY project, In the scope of this project, the idea was to work with a combination of GEBA. The starting point was GEBA and a dynamic hardener from CIDETEC. And our objective in epoxy was to substitute the GEBA. And Caroline explained it was really important to find an alternative. And we developed these two molecules, so the one based on vanillyl alcohol and the one based on fluoroglycinol, and working on these epoxies and on their mixture, it was possible to find an alternative to GEBA, which gives the same properties in terms of TG. It was 130, the objective here, in terms of tensile modulus, and also in terms of impact strength. So this was really interesting. We figured out the best formulation to push further, and then we worked with the partners, and especially CIDETEC, to evaluate the 3R properties. The results are here, and it shows whole aspect of the recyclability that are in the 3R. And also we worked with a tool manufacturer to produce the GEVA and the PhD at larger scale, and we were able by the end of the project to produce 30 kilograms of these resins. And it was used to make something like 40 demonstrators in the field of automotive. It was a panel for rear seat in Fiat cars. A word about Bison project that is ongoing. So it's still based on the Vitrimer approach, but in this case, the idea is to put chemistry into the materials that will help its degradation, but also help an enzymatic degradation step. So the starting point was if you put a thermoset material to an enzymatic degradation process. In this case, because the accessibility into the polymeric network is impossible for the enzymes will only act at the surface and the degradation will not occur properly. So the idea was to somehow have some reversible bonds to be broken by a chemical degradation process to somehow open a bit the materials and give access to the enzymes. So in the scope of this project, we addressed 4 different resins to epoxy, one I would say low TG, 80 degrees, one high TG at 205 degrees, one vinyl ester resin, and one unsaturated polyester resins. So the good news at this point of the project, we are at month 24, we found an alternative, reversible alternative to these 4 resins. And we are, for instance, quite happy to have a Vitrimer with a TG about 205 degrees with the other specifications. And now we produce this molecule. We also work on the degradation process, chemical degradation process, and now we provided the samples for the enzymatic degradation partners for further evaluation. So in the scope of this project, it was the same methodology that the one I explained about how we develop the resin in order to reach these objectives. And in Vibes project, so it's a project that is starting, I think, 18 months ago. It's still the same strategy, working on the reversibility. In this case, it's more geared toward composites. We are working on the resin, the matrix, designing building blocks that are dynamic, but also bio-based. So we try to design new building blocks that combine both aspects, bio-based and dynamic. So to make matrices, it's the same kind of matrices than the one before. And we're also trying to develop, I would say, sizing agents, even if I'm not sure of the term, that can bind onto the surface of the fibers, also have a reactive function with the matrix, and have in the center reversible bonds. The idea being we want to recover the fibers independently from the resin, and so break at the interface the linkages. So this is ongoing, but we are already working and at some interesting results on bio-based dynamic epoxies and hardeners. So to finish my talk, just to give you an idea of what would be the next step for specific polymers. So first, we would like to address more and more thermoset resins. So we are working on epoxies, on vinyl esters, and unsaturated polyester resin. As it was mentioned, it's important to address higher performance materials. And so we already reached 200 degrees TG, but there is some specification at 300 and maybe more. And so first trying to go bio-based on this part, but if we want to go on reversible and high performance, when I say high performance, I mean 300 degree TG. It will be difficult because of the chemistry of the reversible bonds. Then we want to widen our expertise in custom design on resin formulation, mainly trying to reach more and more properties and a wider scope of properties, and also improving our methodology. And for 4 years now, we are integrating a material modeling based approach in order to anticipate somehow the best idea we have in terms of material modeling. So it means putting the chemistry into a software and see what the software say in terms of property. We are not willing to have a predictive measurement, but just to have the main results, the main ideas, and then go experimentally in these areas. And finally, what we want to improve also is the scale-up part, because the solution we are proposing are low TRL solution, and we are conscious of that. And we need to strengthen supply chain to work with other partners that can take what we have been doing at lab scale to bring it one day into the market. So I would like to thank all specific polymer team for their involvement in this area and these projects. I would like to thank Samuel Malburet, who is leading the material and environment activity and really participated to make this presentation. And thanks all of you for your presentation.
Okay, so thank you, Alain, for this nice presentation. I think that we are quite late, so maybe you can ask the questions later, and we will go to the panel discussion directly. Thank you, Alain.
Okay, so now it's time to start with a panel discussion. So the panel will be moderated by Elena Jubete. Elena obtained her bachelor degree in chemical science and her PhD in polymer chemistry. She worked 3 years as associated teacher to polymer technology in Manchester Metropolitan University, and she has been working 16 years in CIDETEC, performing research on different applications of materials, also as coordinator and contributor of several European projects related to transport. She achieved the position of principal researcher in 2014 and BDM of CIDETEC Surface Engineering in 2016. Elena coordinates networking actions, set up new European initiatives, and represents CIDETEC in multiple European platforms. She is also expert evaluator of ADEA agency in Horizon Europe topics. So, Elena, you can start.
Thank you, Nerea. Thank you. Can you hear well? Yes? Now better? Thank you. Okay. Let's try now. Thank you very much to all of you for being here. It's such a pleasure to share with you this end of day with all the participants from the consortium and all the ones interested in this event to show how AIRPOXY is becoming an end and is meeting the results expected to get the materials, these sustainable materials, soon flying. Let's hope so. So today I have the pleasure to finish with a very interesting panel that will represent all the companies that were involved in the development of AIRPOXY project, and also some representatives from the advisory board. So we will start with Caroline Petiot from Airbus. Please, Caroline. Then, thank you, Caroline. Please take a seat wherever you like. Then we will have also with us Molte Frebel from INTA, EREA, from our advisory board, both of them. Thank you, Malte. Yes, I will introduce Malte because I think the CV of Caroline was read before. So Malte is a mechanical engineer and PhD from Polytechnical University of Madrid. Since 2018, he has been professor of investigation at public research institutions and researcher at the Structural Mechanics Institute of DLR, Germany, and INTA in Spain. He is currently head of the Composite Materials Departments of INTA, where he is dedicated to the research and development of composite material structures and fiber optic systems for structural and environmental monitoring in manned and unmanned aircrafts. He's author of several publications and patents and participated in 19 national and international projects. Thanks, Malte. We also will have with us Connor Kelly from Air Composites. Thanks, Connor. Yes, Connor Kelly from Air Composites. He joined Air in 2020. He's a project engineer after graduating from University of Limerick with a degree of mechanical engineering. He managed numerous A2020 projects such as AIRPOXY, also Marwind and Demofact. He carries out tasks related to composite welding, thermoforming, and he coordinates also the work of other engineers, technicians, and operated in Air Composites. Thanks. Okay, and then we'll have with us as well Thibault from SONACA, Thibault De Lumley. Hello, Thibault, please take a seat. I think we were introduced you before. Thank you. So we will continue as well with Emmanuel Detail from CoExpert. Thanks, Emmanuel. Please take a seat wherever you want. Yes. And Emmanuel has a Master of Science in Aeronautics, and since 2013, he has been working in CoExpert as Chief Technology Officer, developing and managing European and Belgian research activities, representing CoExpert in European workshops and exhibitions, and managing consortium agreements, intellectual property issues, and exploitation activities. Before, he was working also for ASCO Industries and Safran Aeroboosters as senior project managers. And hold other positions in Mecanex and European Space Agency. Thank you. Okay, so Diego from IDEC, Diego Calderón, will also join us. Thank you. And I will not introduce him again because, yes, okay. Okay, I think now we are all in. So there is many of the questions that we were thinking about when we were preparing this panel have been already answered because we have already very nice and detailed explanations. But no doubt what the public will like to know is how do you see these developments in epoxy, how they will influence or how they will have influence in your companies? This is maybe the first question that I would like to make to you. Starting, for example, with Emmanuel. Thanks.
Thank you. Just a few words about our activities. So it's really to offer advanced technologies to support the development of new applications in composite fields. So it means that, for instance, we are in contact with the main OEM and tier ones in aerospace sectors. So it means also that we used to work with already qualified resins, but also materials project. And in this case, all aerospace actors are mastering the geometry, but also all environmental constraints linked to the structural part, but also to the aircraft components. And in our case, we are mastering the RTM process. So in this case, I think that if I would have some comments about AIRPOXY outcomes. I would like maybe to come back to the comment of Mr. José this morning, and I think that this new resin formulation is really a good candidate as an alternative or qualified product, and also it could help to improve in the future the manufacturing process. But I think that the development, we need some further development in order to reach outside the market, because as we have seen, the box is quite a closed box today, and if we want to open it, we can of course process, and we have some promising results, but I think we need to go further with this.
Indeed, Emmanuel, it's true. First, we need to progress with higher TRLs, and
yes,
it's
sure.
not evident also in this conservative sector. But thank you very much for your feedback. Thibault.
What I've liked a lot in the AIRPOXY project was the fact that we have addressed a large number of manufacturing processes. And for us, it's very important, because when we develop a new component, we have to select the best process for the specific component. And so it's very good to have flexibility in process selection, because as I said in my presentation, sometimes we want to go to more integration, and it's good to have material that can be processed by RTM, and I'm pretty sure it could be well processed also by SQRTM in the future if we have the right prepreg. But also sometimes we've got limitation and we need to go to less integrated design, and the freer materials can be also processed for a specific process like thermoforming or bonding, welding, that could be suitable for that kind of design.
Mm-hmm. So versatility could be a strong point, right? Thanks. Connor.
Hi everyone. So yeah, the Air Composites, I think 3R resin and AIRPOXY materials would definitely make an improvement in terms of automation, speeding up the process cycle, reducing production costs through the use of the technologies that have been developed, such as 3R thermoforming and 3R welding, which is what I was specialized in this project. Mm-hmm. Yeah, and also the fact that it's repairable as well. Our main area in Aero Composites in Ireland is in aerospace component manufacturing. So we usually have defective parts, and if we were able to repair those defective parts, it would reduce cost and waste hugely. So yeah, yes, that's how AIRPOXY would help improve our company.
Mm-hmm. Yes, the repair, as Diego was mentioning before, I guess it's a very, very attractive issue about these materials. Thank you. Malte, from this perspective of advisory board, what are these potential outcomes that you see more evident to be applied in the aero sector?
Yeah, so from my perspective view from INTA, so as a governmental research center, first of all, this project and this workshop has opened a little bit my eyes, I think. So I showed more or less the same graphics that José Sánchez was showing, so was increase of the epoxy material. And so normally I do not make the dots in going up. I say normally to the people then, okay, maybe it will go flat. But I have not thought about the possibility that it will drop down. So there I really, I was sensibilized these days. So I was maybe a little bit shocked, but this is very good. And so we need to make something. It looks to be clear. And I see from my perspective a very huge applicability in repair. Although it really needs to be well developed. So, I mean, so if you have an impact in a wing or in a fuselage structure, in a helicopter or whatever, and if you have to apply 20 bars of pressure, it is not so easy to do. So, okay, you can press with 20 bars on one side, but then you collapse all the panel. So you must have the counter pressure. You cannot put a whole helicopter in a press. So the potential is there. That's absolutely clear. Of how to apply, how to do it. So demounting the panels, repair, mounting again. There is a future, there's a possibility, but it really needs to be shown how to do it. But the potential is really there. I like this potential a lot. I really must say, I like it a lot. I think it has a big potential there. Also reusability. So I'm working in Spain, but I'm a German, and so I've grown in the 80s. So with this big green tendency of Germany of recycling and so on. And so, sure, I like this of recyclability, and this is really a good way forward. So I'm very, very happy about to see the possibilities that we have there. Again, there we must see how we will do it in detail. So it is not so evident, I think, but the potential is huge.
Thank you. Caroline, please.
So thank you very much. A very good discussion, I think, very open, and many possibilities I could see, and various questions still on my side. Very curious to know about recyclability and reusability. What portion could be reintroduced into a new system? Portion of pristine plus vitrimers in recyclability mode to see how many times we can reuse it. To make it sustainable. Also, question of cost was quickly addressed, to my opinion. So I don't know whether this kind of formulation is cost effective compared. No. So maybe it would be interesting to see what could be done just to make the cost lower in future, to have a kind of roadmap to work on this axis. And then further questions regarding to film addition, in addition for bonding, welding and so on. I had a question mark about the film thickness, whether they could be optimum in thickness, such as to be efficient in bonding, welding, and whether there would be further work such as to improve the situation with potentially activation of surface, and I've got the good specialists there. So fiber sizing was also mentioned. Could we have a sizing using Vitrimer system as well? Could it be a different system?
There are a lot of questions you are launching, so now there is yes. Maybe, well, I can answer the first one, but then I leave the others to complete and comment. But just to help a little bit, regarding recyclability, it's an issue that is true that it was not deeply studied in this project because it was not the purpose of this call we were targeting, although we know it's one of the highest promising characteristics of the 3R material. But in line with this, we have currently started new actions. Between them, we have, for example, a European project that we have just signed now that is called MC4, where we will be starting to analyze to develop, or let's say not to analyze, to develop further the two potential routes for recyclability of 3R materials. We have also some other collaborations with industrial partners that are interested in this property of the system. So it's an aspect that CIDETEC is targeting at the moment. And yes, as mentioned, it was not a core in AIRPOXY because AIRPOXY was more oriented to manufacturing. But yeah, it's one of the key challenges. And yes, as for cost, it's something that we need to work on with the economy of scale as well. So we hope that in the future it could be, if we consider recyclability and reparability and all the outcomes and advantages that the material can incorporate, it will be able to be almost comparable to current epoxy systems. But this needs to be already taken into account economy of larger scale production. At this stage is not the case. I have to be clear. But yes, I think Diego will help me to continue answering some of the other questions, or perhaps he launches some more.
No, well, I would like to give us our vision from only RTM producers, so manufacturers with the flexibility in our case is not so important, but the key for us is the repair capability. As has been said several times, there's a lot of work to do, because we have said during the project that it's not possible to apply 20 bars in service. It's quite difficult to do it in our workshop after manufacturing, but it seems that there's a way to do it. And I would like to be more optimistic right now and try to be more or less in the consortium. We know the answers, I guess. Why it has been so difficult. There are some ways to modify the resin, or maybe target another kind of TGs in this case. I think that's the point, and we have discussed it sometimes here. We must open a little bit our minds, and maybe it's not necessary to have a TG of 170 or 180 for a part that is structural analyzed at 70 degrees. Yeah. So we are launching stones over our heads. So maybe with a TG lower, everything is easier. We can repair with lower pressures, and let's see. I encourage everybody to follow these investigations with more proposals, more projects. For sure, we are open to collaborate with all of you. And for us, the capability of repair, it's a change of everything. As I said, we have been talking about reduce of cost of scraps. And I said a couple of examples where we have scraps for minimum defects that can be solved easily with some pressure and heat. So that's a way to do it, and I think we can do it.
Thank you.
So I think just in your case, it is easier to apply the pressure. So the first part is, so you said, so when you have a damage or delamination that's bigger than 2 by 2 centimeters or something like this, you have to reject the panel. Okay, at least you know. So there is a place, 2 by 2 centimeters, or 4 square centimeters. And when you need 20 bars of pressure, then it is 20 by 4. So in kilos that you have to put, so you put 200 kilos, then you have the pressure. Okay, you cannot do it on a big scale. So, but if you have really a small scaled, well-known delamination in one point, and before throwing the panel away, there you could apply. So there I really see a possibility.
Then we need to be allowed to do that, and that's where Airbus and quality and so on enters. And
the science and the politics always go together, or need to go together.
Yes, but I think there's also a good way to work there. Validating repairs, validating methods of acceptance of failures and so on. It's so strict always. I agree with Arnova that safety first, but okay, safety first with some rationale behind. You must know why are you rejecting a part. Okay, I think that's a good point also.
Yes, indeed. I also wanted to ask you about the potential for recyclability, as we have seen that there is so much interest on this capacity in the material. How do you see that this could open opportunities as a main result of these rare materials? So any volunteer to start with?
So I think it's quite encouraging, and you are on a good track. If we can reuse a good portion of the material to make sure that the performance won't drop, so we need to find this optimal, let's say, in the formulation, in the ratio between pristine and recycled part of material. And also the question is, how confident are we? Can we have retrieve the fibers with very clean surface, or do we still have some elements of the resin which would remain fixed on the fiber because of the sizing? Okay, we need a new project, I think.
This is the beginning of the of our research line in the recycling part, so we'll have a answer soon, we hope, and probably we will invite you to our next final workshop to share these answers. Let's hope so. Okay.
So I think the recyclability of aeropoxy materials will help, especially Air Composites, in their strategy towards sustainability. I think it's a real attractive aspect of aeropoxy materials. In terms of tendering for manufacturing more sustainable products and components in all industries in the future. And I think it's a unique selling point as well in that respect.
Thank you, Conan.
On our side, we are concerned about the downgrading of the material performance and value when we do recycling. So we would first start to find ways to reuse material scraps that we have during manufacturing in order to be able to use that material to manufacture aeronautics components with better performance, I would say.
So you will probably start from the reuse at manufacturing, no? From such scraps, because it will be the first point before end-of-life material. Maybe it's easier to start from such scraps, right?
Yes, or end-of-life, rather to try to reuse components or part of the components to remanufacture new aeronautics structures, rather than recycling. I understand the importance of being able to do recycling, but in our mindset, I would say, yeah, the downgrading is an issue.
Yes, indeed. Mm-hmm.
Yes, maybe some inputs that I would like to add. So in our case, we start from the beginning during the design for manufacturing phase to optimize the use of material. So it means that at the end, it's less scrap, less waste. And also more and more, so I think that everyone learned about Industry 4.0. So now we have some current development activities, which the target is to collect all process data. And so it means that we would like to be able to develop a means, thanks to artificial intelligence, to support, for instance, the operator to take the right decision at the right moment. So in this case, that you are able to avoid maybe any deviation during the process. It means, in this case, for instance, you can stop the process and, of course, replace the manufacturing or replace the preform, or avoid any scrap at the end of the production line.
Mm-hmm. Indeed. Thank you, Emmanuel. This point of circularity from the design phase is becoming more and more important, And it's true that if we don't take note of this from the beginning, there will be still many problems in recyclability aspects. So I appreciate this note, and I think it's something to be considered. So for sure, with 3R materials also, the fact of designing them for this purpose, I think it's a good contribution as well in that area. Thank you very much. I think there was some people that wanted to make questions in the audience. If so, this is the right moment. We have the panelists ready for some additional question, if you are willing to. Please, Lydia. I will bring you.
Thank you, Ellen. Hello? No? Well, I can raise my voice. Hello? Okay, now. Okay, they are recording. I'm Lydia from ITIP. It's been really interesting, what you have been discussing today. I have another doubt, because we have been discussing a lot about recyclability, circular economy, and the end of life. But as we have seen, and Jose was mentioning in the very beginning, that in the future we will have a combination of thermosets, thermoplastics, and metals, which are rising again. And I think that Miguel Ángel has shown a mix of a titanium with a carbon fiber thermoset kind of part in the presentation. About the lack and availability of these components, of these metals, with the kind of crisis that we have had in a lot of industries. And I don't know how it's affecting really to the aeronautical sector, and what is your vision in this midterm and long term in this lack of availability of these materials, and how can we solve this? If maybe it's an opportunity for bio-based components to substitute some of the chemistry of this titanium or these high-tech metallic components that are not, the source is not in Europe. We have to import it somehow. So it's also a new variable in the equation, no? So I was just wondering what's your point of view on this?
Thank you, Lydia. Very good question. Any volunteer? I think Thibault is thinking hard and maybe want to...
Yeah, it's, to be honest, very difficult question for me.
Sorry.
No, anyway, I think lots of materials are affected by the current crisis, because we've got lots of difficulties in material supply, not only in metallics but also on the composite side. And so maybe it can help open discussions and reflection for the future, but developing new materials, bio-based materials, takes very long time, so we are not on the same time scaling also. So I'm not sure it will have that significant impact on the topic.
I'd just like to make a point. I think this will encourage legislative enforcement to try and encourage us to move towards more recyclable materials or bio-based materials quicker when you come across global restrictions or supply chain issues. So I think, as Elena said, politics and science go together. So I think legislation will play a part in that.
Indeed.
Yeah, so I think so in some of the metals, it's a question of energy. So aluminium, I think there's enough, the raw aluminium, but you must have the energy to get it out. So it is very energy consuming. In this case of the metal raw materials, I see there's a much bigger issue in electronics. So there's we are depending so much in Europe on China and on other countries. So there's a big issue with the normal metals. I really okay, titanium can be also a little bit a problem with normal aluminium for this. I do not see such a problem, but I'm absolutely no expert, so I do not have an idea. I give it to you.
Okay, well, just one comment. I think it reinforced regarding the Six Waste Directive from the European Commission. It reinforced the fact that we need to sort and be able to segregate those materials, separation between plastics and metal. And I think it's pretty much important because the prices are increasing. Like if you look over to copper or other kind of material, silver, like used in electronics, it's really important to do that. Also, rare earth materials, we are highly dependent, as you've mentioned. We're critically dependent in some of the materials. Cobalt, for example, is one of them. And we want to move towards more electrical aircraft or battery system. So this is in the short term. I think it's an opportunity for Europe really to give a push for the sorting, segregation of what we have already at disposal. Then for the rest, it's a complicated question because it's linked to the geopolitical situation worldwide, and we don't know how things could evolve, and materials are competing. So let's see.
Well, from our point of view, we don't have problems of supply for the moment. But as I said before, we only have a system of materials. Fortunately, I think it's manufactured in France. But what's happened, or what could happen if there's a big strike in France and we run out of material, we don't have any alternative, so any alternative could be welcome for sure. If it's cheaper, better, and as close as possible from our workshop or the site where it is manufactured. So I think from my point of view, the globalization is over in this case. I think there's an evolution in this movement, and Europe has an opportunity here. So we must push again and try to find alternative solutions. The thing is to have alternatives and not be tied to only one supply. It doesn't matter if it's from France, Germany, or Belgium, but you have to have alternatives and choices. Yes.
Okay, I have one last question in relation to the complex structures where this material, the 3R, could be incorporated. No, since as you know, part of the project was also in line with bonding strategies and having also 3R material as adhesives. So, what are the challenges you have encountered in this regard, regarding the joining of a 3R composite material to other different type of materials, either other composites or metals? What is, in your opinion, the most challenging that can be worked further, or the advantages that could bring also the 3R materials as adhesive materials in the project?
Well, I answered just because I have the microphone, but
thank you.
We didn't have too much experience with the adhesive. But we didn't find it difficult. I think it was let's say, a standard process, and then we did some trials about the repair of the adhesion, and it seems it worked. So it's okay. It's as I say, in one micrography we have some porosity that it must be solved, but again, there's a potential there if the repair can be then repaired, because as Jose said again in the first, the joints is a key point always.
Exactly.
All the structures at the end must be riveted, because nobody trusts in the bonding joints. So there's again a field there, and if it can be repaired, again, it's a strong point.
Yes, the question is whether it could be an entry point, such as to replace adhesive in some specific location, just as an entry point, and to show that the system could be as effective as other adhesive today, such as to its dismantling. This is already one step. I think could be an opportunity to get something like that. Also to mention the lower TG of actual current adhesive system for aeronautics. Again, it could be in favor of the 3R systems because it would reopen some gaps between the TG and the temperature of transformation. But it should be proven that we won't face some creeping effect in over the duration. You've understood. Check it because it's a question.
So I'm not sure, but I think if you weld two materials together that are made from the same material, then you do not need these chicken rivets. Only you need this if you bond it with an adhesive layer. I'm not sure. So, José.
Wait, José.
This subject is a very interesting subject. We opened a discussion with Larry Ilkevich from FAA about this. What is the meaning of co-bonding, co-curing, and secondary bonding? Secondary bonding is obvious, but the other two know. And this is a very interesting discussion. What is the limit? And thinking about this, we even developed some material that can co-cure, between brackets, with other material. So we arise the question to FAA and EASA, it is really a co-curing or is a co-bonding? If it is a co-curing, will we avoid the rivets? So it's an interesting subject under discussion with our authorities. I think Timo, I am here with Timo. We are discussing this, and it's something that Airbus is still interested to continue thinking about this and even change the regulation for this. So the concept that you saw here opened the possibility to avoid this co-bonding name and to go more for co-curing. This will facilitate the application of the part.
So if there is, sorry, Connor, please, you wanted to.
Yeah, just in terms of the challenges and bonding 3R materials, as I have some experience with 3R welding, initially IVW were developing induction welding, but in terms of complexity and material properties, it didn't really work out too well. So we moved towards the conduction welding route, and that still, although we demonstrated that it was possible to conduction weld, the quality wasn't great. So I think, as Thibault outlined in his presentation, that in terms of future steps with 3R material and including different additives to try and make it more dynamic, and maybe the removal of the 3R film and just having without bonding or welding without having any resin film in there at all may be better in the future and more sustainable than having consumables in there. So yeah, I think that's a challenge in itself.
Thanks.
Well, at SONACA, we have done lots of bonding in the past, mainly on sandwich structures. But today, for the reason that was mentioned this morning by José Sánchez, we do less sandwich and we go more to monolithic structures today. And for that, we prefer to avoid bonding for surface preparation issues, for the difficulty sometimes to control and to inspect the quality of the bond, and also for the problems mentioned about the need of chicken rivets. So we prefer to do either co-curing or rifting if needed. So, but in the project, that's why we were more interested in the welding capabilities, because we think that this kind of process, if it could work, would be more robust to the issues I've just mentioned.
Understood. Thanks, Thibault. Emmanuel.
Yes, just to complete, yes, the reply of Thibault. So LTM or SQLTM processes, when possible, are really a good candidate to avoid any further bonding or I would say post operations. As Thibault said, you just need a one-shot injection, and so you don't need post-operation as rifting, bonding with next further occurring operations. It allows also to reduce labor, also to optimize the manufacturing process time and so on.
Excellent. Yes. Okay, so I think unless somebody else want to make a last question. Okay, last one over there.
What is the commercial status and reach status of the curative, the disulfide curative?
Sorry, can you repeat
the
again?
Commercial status of the curative. Is it commercially available by chemical manufacturers?
You mean the hardener,
Yes.
right? Yes. If it's commercially available?
And at what scale?
Yes,
What
it's
scale?
a commercial molecule that currently is not used for this purpose.
But
Before
at
our
what scale
research,
what scale is it available at the moment? What scale?
What scale? I don't know the exact scale, but I think at the moment it is not used for such a large manufacturing applications. So if the 3R composites succeed, of course, there will be a need to upscale this material, and also this will be the reason why the price will decrease also significantly. So indeed, it's a potential, and it's an opportunity that is there, open, in order to make the technology close to market, let's say. So at the moment, it's still produced not in a very large scale, let's say. I cannot tell you the volume, maybe 100 kilograms, they say, yeah.
The current limitation is that this hardener is not yet reached register. So 1 ton per year is the maximum, but you can buy 1 ton per year. There is not a limitation because of production scale. This is commercially available. So for the project, we have buy it in 100 kilos.
Thanks. So, anything else? Okay, so I think we are ready now to start to see the demos and to initiate the visit also to CIDETEC Surface Engineering. So, please, Nerea.
Yes, so we are a little bit late, so we will proceed with the visit and the visit to the showroom and the visit to CIDETEC. So we are going to split the audience into groups. I will name some people, so the people that I name now will be in the first group, and they will start the visit here at, to the showroom. And then the people that I don't name, they will go to visit CIDETEC. Okay, so Elena, you pick up the people that I don't name, and the people that I name, you can go to the showroom. So people that will start with the showroom are José Javier Regurrola, Elena del Puerto, Martín Simons, Professor Baris Kumru, Berta Gonzalvo, or her replace, Alejandro Batán, Eric Hernández Edo, Pablo Martínez, Elena Rodríguez, Alain Graillot, Miguel Ángel Castillo, Andrés Catalán, Nora Feiden, Juan Pedro Berro,
Emmanuel Detell, Maria Cosarli, Alkis Paipetis, Peter Michan, Connor Kelly, and Diego Calderón. So all of you will be here, and the rest you can go with Elena to visit CIDETEC, and afterwards we will change the two groups. Thank you very much for coming. I would like to thank to the speakers. Sorry, Timo, can you move a little bit? I would like to thank to the speakers for giving us such nice talks, so well prepared talks. I would like also to give thanks to the AIRPOXY partners. I think that, well, after 4 years we have finally performed very good work. And finally also I would like to thanks to the organizers for supporting me with all these sessions and event. And finally thank to all the attendees, and well, I hope to see you soon. Thank you very much.
I wanted also to join these thanks, because I think the best we did in the project, I mean, this team made very, very good things. I'm happy to be able to have seen all the process. But one of the best points was the selection of the consortium. I think we have been very lucky to count on all of you to be so involved and collaborate. It was a pity we couldn't meet more, because with the COVID it was just 3 meetings. We have the chance to meet physically, but indeed we have been very lucky to keep these excellent partners involved in AIRPOXY and make this a success together. Thank you all so much. Okay, so I think we can close the day, no, Nerea?
Yes. We can close, and I wish you all a good trip back home, and see you in other event. Bye bye.